And and it's a nice occasion actually to talk about quantum Monte Carlo, right? So which is which is the main technique we'd like to study during these days, and it's supposed to be worthwhile using it, and hopefully we convince you that that it is really worthwhile. So the outline of my presentation, so that's the outline. These topics covered today will be sort of inspired by the features TurboRVB has in its own development and its own the foundation of TurboRVB rely on the topics I'm going to cover today. And one of the main topic is the wave function, the correct wave function. And one of the unique features of TurboRVB is which is the heart of the code and which gives the name to the code, is the just correlated geminal wave function. Okay, so since the beginning, the code has been built around this wave function for different reasons. I mean, we're going to see the reasons a little bit today, a little bit tomorrow, because one of the first goals, long-term goals, was to study eventually superconductors, and the just correlated geminal is sort of a wave function realization of the RVB ansatz proposed by Anderson in the 80s to describe Couperet superconductivity. So, and that's why, the code is named like TurboRVB. Turbo because it's meant to be very fast, efficient, and super fast, the fastest possible realization of the RVB in the quantum Monte Carlo. And RVB is the wave function, which is basically the heart of the code. And another name for this resonating valence bond wave function, so RVB stands for resonating valence bond wave function, is the just correlated geminals. Okay, so just correlated geminals is another way to call RVB. Okay, so the first part will be about this wave function, and we're going to start again because I have seen it many times, I guess. What we mean by the many-body problem. I'm going to start to introduce the just correlated AGP, antisymmetrized geminal power, geminals. I'm going to start by looking at a very simple problem. Everybody has seen this at, I think, already at bachelor level or master level, the hydrogen 2. Okay, so hydrogen 2 can be seen as a maybe very easy and very boring problem, but it will be useful for me to introduce step by step the ingredients necessary to understand what is a geminal wave function and what is a just correlated geminal wave function. Okay, I'm sorry if I'll be too simple and maybe too trivial, but that's the way basically I took, and actually, to be honest with you, this is the way Sandro used to introduce geminals last year. So Sandro Sorelli was supposed to give this lecture, and I'm replacing him, hopefully, trying to reach sort of his expertise and his sort of knowledge in physics. And unfortunately, he couldn't come here today. So, but that was the way Sandro used the last year to introduce geminals. He took this problem, and I found this choice appropriate. So I'm gonna basically repeat. I'm gonna follow his path, and I use again this H2 as a sort of simple toy model to understand the physics of geminals. Okay. So yes, so I'm going to start from the zeta determinant in the H2. Then I'm going to introduce this the geminal, which are in the fermionic solution. should be antisymmetrized, so they're called antisymmetrized geminal power, the type of geminals used in the fermionic framework. And this will be the elementary brick to construct the variational wave function, which is just correlated as well. And finally, along this journey, I'll talk about the parameterization of the wave function and the use of our localized basis set. Okay, you have seen this already, I think, with Claudia and Anthony, because also Champ uses Gaussian localized basis sets. So this will be already a topic covered, but I'm gonna repeat it anyway. So I think repetita juvent, as Latin said. So I'm gonna repeat maybe already other comments. But if you have any questions, or if you find the things I'm telling you trivial and straightforward, please let me know, and I try to adjust the presentation according also to your sort of your wills. So the second topic is about the wave function optimization. And so this will be divided in sub topics. So I'm gonna give you a recent overview on the stochastic optimization of the wave function, and I'm gonna introduce some basic methods. One is the correlated sampling. Then an important point of to optimize the wave function is to compute the derivatives, energy gradients, and that will be another topic covered here. And then I'll introduce the stochastic reconfiguration, which is again another feature of TurboRVB. So TurboRVB was one of the first codes which included the stochastic reconfiguration method to optimize the wave function. And finally, related to the computation of energy gradients, a particular gradient of the energy is the ionic forces. So when you derive the energy with respect to the ionic coordinates, you get the forces. And so, but forces require some care. So there are some details which are not trivial, should be taken into account. And so this will be the last topic, the ionic forces evaluation. Okay, so let's start with the many-body problem. So we'd like to solve the Schrödinger equation, including the interaction between electrons, which is this one, between electron and nuclei, and between nuclei. Okay, so we have that's a quantum mechanics foundation. So you have the kinetic term for the electrons here, and the kinetic term for the ions there. So the first remark on this equation has been done by Dirac, and I think you know this very well because it's a very famous sentence cited many times. So we know everything because the theory we have laid down the theory. So we know the fundamental interactions. We know how to write the equation which govern the materials properties and essentially what we experience in our world, because I mean materials surrounding us. But there is a little problem, okay, and that's the only difficulty of this is that these laws are too complicated and to be solvable exactly. And so it's desirable to have approximate practical methods. Okay. And so if you read this sentence, it seems to be that having approximate practical methods is just a side issue. It's not the main stuff. I mean, we know the equations, so we are happy. I mean, from our perspective, that's exactly the challenge, right? The challenge is to be able to devise approximate methods which are practical and which are predictable. Okay, that's the main point. So we'd like to predict, we'd like to explain the main features of complex atomic systems. Okay, and so the first attempt to simplify the equations, to have these approximate methods working, is to neglect the quantum moments of nuclei. Okay, so if you neglect the quantum moments of nuclei, then the nuclear coordinates are just parameters, input parameters, and we'd like to solve for the electronic part. Okay, but still, even with frozen ions, the problem is very hard, and that's why we have the richness of quantum chemistry, the richness of density functional theory was deployed to tackle the many-body electronic problem, and we are still at the stage of struggling with it. Okay, and there are many problems in condensed matter physics and quantum chemistry which are not understood just because we don't have the tools to understand them. Okay, and quantum Monte Carlo is supposed to be one of these tools. Maybe I don't know if I'm there to be the best one, but it's one of these tools. This is the sort of the definition of the notations I'm going to use in this series of lectures. So capital R will be the ionic coordinates. Okay, R and sigma will be the electron coordinates and the spin of the electrons. Sometimes X will be used as generic spin or coordinates, position and spin of electrons. And we're going to use a framework, a canonical framework. So it means that the number of particles is conserved, is fixed, is an input, it's again an input, and up is the number of spin-up electrons, and down is the number of spin-out electrons. I mean, this seems to be trivial sentence that we are using canonical ensemble, but in condensed matter physics, maybe not in quantum chemistry, because in quantum chemistry are just finite systems. In condensed matter physics, that's a strong hypothesis, okay? Because usually also you work with systems where the number of particles is not fixed or is fluctuating. And that's the TurboRVB conventions. I think it's convention used also in other codes. The first and up coordinates and spins are for the spin up electrons, and the last part of the string of the vector is for spin down electrons. That's the order used in TurboRVB. Okay, so the Fermionic wave function must satisfy the Pauli principle, so should be antisymmetric for the permutation of any pair of electrons. And our specific goal is to look for the ground state of the time-independent Schrödinger equation. Okay, so that's our goal. So again, we are sort of reducing our sort of to-do list, because in principle we could also be interested in excited states. Okay, and I think you have seen excited states yesterday. Huh? But here we're going to focus on the ground state, which is already a difficult problem. And from the ground state, you can learn also already many things, many properties of the system. Although there are some properties which are intrinsically dynamical. But so for let's say static properties and sort of steady states, the lowest energy states, we're happy with the ground state. Okay, so a way to tackle the many electron problem is to resort to mean field theories. Okay, so in the mean field theory, basically you make the electrons non-interacting. And why is that? Because if you have a non-interacting Schrödinger equation, you know how to solve it by diagonalizing it exactly. So you can diagonalize it, and you get the eigen vectors and eigenvalues. the phi I orbitals, which are the eigen orbitals, and EI, which are the eigenvalues for both up and down electrons. And so, many methods aim at deriving good mean field Hamiltonians. Okay, where now the mean field potential includes implicitly the interaction of the target electrons with the target electron with the surrounding ones, so the other electrons in the system, in a self-consistent way. Okay. So there are different, there are different mean field methods, right? DFT is one of them, and between DFT you have different mean field potentials you can get according to the type of functional you use. So these phi I, which are the eigen orbitals of the mean field Hamiltonian, are called molecular orbitals. Okay, so just I've seen this already, I think, with Claudia and Anthony. So I'm sorry for these, for those connected through Zoom. All right. So I was saying that yes. So if you literally follow the recipe of the antisymmetrization operator, you get an exponentially large number of terms, right, and factorial terms. But thanks to the linear algebra, we know how to compute the term. So the antisymmetrization can be recast into the determinant, the Slater determinant of a matrix, written in this form here. And we know how to compute the Slater determinant of a matrix in a polynomial cost n cube. Okay, so thanks to this feature, we're able to antisymmetrize the wave function, which will cost formally and factorial terms, into a polynomial n cube cost. That's a great advantage. Okay, so we should be really happy with that. And although we complain, right, about this n cube, we'd like to go linear scaling, but it's already a huge improvement with respect to the original antisymmetrization operator. Okay, anyway, so let's take now the H2 problem. Okay, so we have two nuclei sitting at R1 and at R2. We have two electrons, so it's a neutral system. And we'd like to solve this first with Hartree-Fock theory, so in a self-consistent way. So by diagonalizing the Hartree-Fock Hamiltonian, we get as eigen orbitals, eigenstates, bonding and anti-bonding orbitals. Where now the bonding orbital is the one depicted here, okay, which is symmetric by the exchange of the two ion, and the anti-bonding is the one with the minus sign in the case you expand this in terms of atomic basis set. Okay, and so the bonding is the lowest in energy. So the spectrum, the one-body spectrum, gives the bonding as the lowest energy state. And of course, the self-consistent, in this case, the self-consistent potential will have a Hartree term, which is given by the electron density of the other electron, which is described by the 5b squared, right? So in this, you can see the self-consistency here because the eigen state of the operator enters also in the potential. So you should solve the Hamiltonian self-consistently. And now if you take the two electrons, you put the two electrons in the lowest one-body level, phi b, you have to take into account the fact that the wave function should be antisymmetric. So you're going to put an up electron and then down electron in the same state. And if you plug now this into the zeta determinant, you get that you recover the singlet state of the ground state. Okay, so the ground state is a singlet, so up down minus down up times 1 over square root of 2. That's the spin part, and the spatial part is just the product of the two equal one body orbitals equal for up and down spin. That's the Hartree-Fock solution. If you study now with Hartree-Fock, yes. No, there is no exchange. Yeah, that's a very good question. There is no exchange because we solved the problem in the singlet manifold. And in the singlet manifold, you don't have exchange. So if you can do the same exercise, the mean-field solution in the triplet manifold for the two electrons, and in that case you get the exchange. But the lowest energy state of the singlet manifold is lower than the two electron state of the triplet, despite the fact that you have an exchange term, which is negative, right? Which is lower than, because the kinetic term is the penalty you pay in the kinetic term is larger than what you gain in the potential term. So that's the interplay between potential and kinetic contributions. So you pay a cost in the kinetic contribution because you have a node in the triplet solution, which costs more than the gain you get in by the exchange. But in the ground state, in this case, you don't have exchange because you are in a singlet manifold. Okay. Right. So that's a very good point. So you see the H2 is not that easy. Okay, anyway, so I mean you can learn a lot from H2. So if now you'd like to study the dissociation of H2, okay, within Hartree-Fock, you discover that, and you follow the singlet solution. Okay, that's another point. You'll discover that this will dissociate to a much higher energy, okay, than the sum of the two independent hydrogen. Okay, so this is wrong. Okay, and you pay an energy which is unphysical. And by the way, so the dissociation of H2 has been used by many other methods. So I have seen many talks, for instance, in GW community. So they are also in also in the FT community. So getting the H2 dissociation right for the DFT GW community has been a huge deal. Okay, and that's really a test bed for correlated methods, or for sort of improved DFT functionals as well. So I can anticipate the solution. So in quantum Monte Carlo, it's basically trivially exact. Okay, so I mean, for us, for the quantum Monte Carlo community, H2 is, is exact, basically. So is exact. So I mean, the difficulties in quantum Monte Carlo come later a little bit. Okay, but you know, that's basically a problem we know how to solve exactly very well. In contrast with the different methods like DFT or GW as well. Okay, anyway, so let's go ahead. So why we have this failure? Why the Hartree Fock fails in the limit of large dissociation? So let's go back to the bonding orbital, okay, constructed as linear combination of atomic orbitals. So that's the bonding orbital is the plus sign, right? So it's linear combination with the plus sign, symmetric by the two ion exchange. So you're going to see that if you populate the bonding orbital with the up and the down electrons, it can happen that both electrons sit at the same site, because they both have probability of sitting at R1 or sitting at R2. And so this is the cause of the failure, the fact that you allow for some double occupancy of the single ion. Okay, in the wave function there is no way to the Hartree Fock wave function. There is no way to damp these contributions. And so, yeah, so the failure is the absence of correlation at short distance. Okay. And that's why, actually, if you go back to this slide, that's why the penalty here, the barrier was reported as U half, because U is sort of the local repulsive term. You pay with this wave function. Now, can we get a better Slater determinant? How can we improve upon this Slater determinant? So we used so far the 1s orbital, okay? The 1s orbital of the hydrogen atom. So we can improve the Slater determinant by expanding my bonding orbital into a better basis set. Okay, so and the basis set, I can take the Slater basis as the ensemble of all one body, all eigenstates of the hydrogen atom. Okay, so this defines my Slater basis, and I can improve the description of the Hartree Fock by expanding my bonding orbital not only on the 1s state of the hydrogen atom, but also on the 2s, 2p, higher energy state of the single atom problem. And actually, the bonding is not only expanded over one side, but it's expanded also on the other side. So you have two sides, right? So I expand on both site 1 and site 2, and already site 1 for site 1, the full set of hydrogen eigenstates is a complete basis set. It's even more true if I have two sides. Okay, so if I have two sides, I have an over complete basis set. Okay, so in any case, I'm going to improve my bonding orbital by expanding over a more refined basis set. But still, so I mean, yeah, so that's the definition of Slater terms, Slater basis. You have seen this right many times. I think it's not. I don't want to spend too much time on that. Then there is we can also choose the Gaussian basis set, Gaussian type orbital, which have this shape here instead of the Slater. You get really. So the radial part is a Gaussian envelope. However, even if I improve the one body basis set, I have still a problem of double occupancy. Okay, so I can improve the shape of my bonding orbital, but I will still have two electrons sitting on the same orbital and having the probability of being present at the same ionic center in exceedingly large way. So I have still a problem of double occupancy. Okay, so so improving the one body basis set doesn't help. Okay, I should do something else. So what I can do, I can just look at the problem. I look at the ground state shape. Again, it's a singlet. Okay, so I can stay in the singlet symmetry for the spin, and I have this G function here, which is a function of two coordinates, of two electron coordinates, and this G is called geminal function. Okay, so it's a two-body function, and this is the analytic form, which is the exact analytic form of the ground state for H2. Okay, and so what is now the shape, the form of G in the R3 Fock? In the R3 Fock, this two-body function is the product of one-body orbitals. It's the product of the one-body bonding orbitals. But that's, you can see that this is just a specific choice for G. I can do much better. Okay, I can improve the two-body part a lot by going beyond this form. Okay, and so that's the key point here. The key point is that I can recast the green function of H2 in a singlet times a two-body function, and by improving upon the two-body function, I can go beyond R3 Fock. And this two-body function is called geminal. Why geminal? Because it's a pair function. So it's called a pairing function or geminal. So because it involves two particles, two electrons. Okay. Okay. So now let me rewrite again. So I'd like to analyze again the source of the origin of the problem in the R3 Fock. I'm not going beyond R3 Fock yet. Okay. I'm just setting the background, the framework. So if I rewrite the R3 Fock, okay, in terms of the product of two bonding orbitals, the two bonding orbitals are linear combination of atomic orbitals. I have phi1, 1, phi plus phi1, 2 for the first bonding orbital, and phi1, 1 plus phi1, 2 for the other one. So the same, right? So what is phi1, 1? Phi1, 1 is the 1s orbital sitting at R1, and phi1, 2 is the 1s orbital sitting at R2. Okay, sorry, it's a little bit heavy notation, but okay, I realize this. But so they are just the two atomic orbitals sitting at R1 and R2. So I take the linear combination of these. So what I get now, if I expand this product, I get terms where now one electron is sitting at the left-hand side and the other at the right-hand side, and vice versa, because there is the symmetric permutation. And I have also terms where two electrons are sitting at the left-hand side, at the left ion, or two electrons sitting at the right ion. Okay, and so those are atomic or ionic contributions which cost a lot in terms of energy. So that's exactly the terms. Oh, sorry, the terms I'd like to tune. I would say remove. Okay, but maybe I'd like to tune. Maybe those terms are not, you know, they cost energy, but maybe they could be helpful, but not with the weight provided by R3 Fock. So if I remove these terms, I get completely, I get the Heitler-London solution. So the Heitler-London solution of the H2 is the solution where I removed completely the ionic or atomic contributions. Okay. So now let me introduce the geminal written in the most general form. So I'd like to be very flexible. I'd like to develop the geminal in the most flexible way. And so how can I do that? I just developed the geminal in terms of a two-particle basis. A two-particle basis is the product of single-particle basis. Okay, and I take all possible products in this basis, and I tune and I weight each term with this lambda coefficient. Okay, so that's the complete. It's a complete basis set in the two-particle basis, and I develop this the geminal function into this complete basis set with the coefficients lambda. Okay, that's the most flexible pairing function, and if I'm able to optimize these lambdas, I get the exact solution for the H2 already at a variational level. Okay. And my orbitals are localized orbitals. I'm in the framework also set up by Claudia and Anthony previously. So this wave function is expanded on localized either Slater or Gaussian orbitals. Okay. I can do something. I can do a step farther. I can make a step farther. I can diagonalize this lambda matrix. Lambda is a matrix. Why? Because the entries of this matrix refer to the indices of the two-particle basis set. Okay, so ij, the basis set for one electron and the second electron. So if I diagonalize this lambda matrix, I get a diagonal form. Okay, and yes.
Can lambda be symmetric if the atoms are not identical? I mean, not H2, but the CO, the different atom. Is lambda symmetric?
Yes. So even if the atoms are different, even in the polyatomic system, the lambda must be symmetric, although the expansion will be much more complicated. Okay. In this case, the lambda is can be I mean, depending on which basis set you use. Okay, so the size of lambda depends on the basis set. Okay, so in this case, written in this way, it's a 2 by 2. Okay, so if you take these as localized atomic orbitals, it's 2 by 2 because I have also the summation over the ionic indices. So I have two ions. Okay, so for each electron, I have the 1s component or even higher energy components, 2s, 3s, and also I have the ionic components. So electron 1 can stay in, let's say, let's take just the 1s component, the smallest basis set. I can have the 1s sitting on the left ion, the 1s sitting on the right ion. So for each one body basis, I have two components. Okay, and yes, so that's 2 by 2. So yeah, so because going back to your question, the symmetry. So the symmetry of this matrix is due to the electronic transposition here. Okay, so and this is sort of independent on the setting of the system. Okay, so it's electronic symmetry. So as we are in the singlet manifold, the singlet sector, the singlet is antisymmetric from the spin part. Okay, and so to have a fully antisymmetric two-body spinor, I have to impose a symmetry in this spatial part. So it's antisymmetric in the spin sector because it's a singlet, and so it should be symmetric in the spatial sector. Okay, All right. So I can diagonalize it, and I can get a diagonal form. And now the orbitals in this diagonal form are molecular orbitals. Okay, so those are linear combination of atomic orbitals. Okay, so I don't know if it's clear. So I can go from an atomic expansion to a molecular orbital expansion. Yes.
You have a question?
Lambda. Yes, I answered this already. Yes, yes. So in the yeah. Now, so this is very important because from this diagonalization of the geminal expanded over atomic orbitals, I can get some physics, because the molecular orbitals reflect the nature of the chemical bond. So by diagonalizing this, I get this form which encodes some physics as well. In particular, I'm gonna get the bonding anti-bonding orbital again. Okay. Okay, but in this case, the bonding anti-bonding orbitals will be weighted differently. So the weights of the bonding anti-bonding orbitals will depend on the specific weights, specific coefficients I get in this expansion here, which is flexible. Okay, I don't have anymore the either London choice or the Hartree-Fock choice. I'm more flexible. So by looking at this expansion in the molecular orbitals, I can sort of classify my geminals and sort of I can classify the correlation level, if you like. So if in the H2 only one of these coefficients is different from 0, so if the first one, I have the Hartree-Fock solution. So the Hartree-Fock solution is the expansion in molecular orbitals where only the first state has a non-zero weight. Now, if I have also a linear combination with the first term plus other terms, then I include the correlation. Okay, I go beyond Hartree-Fock. So going beyond Hartree-Fock in the geminal expansion means for the H2 having coefficients different from 0, not only for the first MO, but also for the next MOs. And so I can see from this shape, from this form, what is the physics of the system and what is the correlation level. Okay, so you can see here one property that this wave function, one of the limits of this wave function is Hartree-Fock. Okay, so the Hartree-Fock is included in this ansatz as a wave function where I have just one coefficient different from 0 in a case of just one pair, or I have n-half coefficient different from 0 in the case that I have n-half pairs in the system. Okay. Yes. So the question is, are we expanding molecular orbitals using bonding and anti-bonding orbitals using different weights? Okay, so again, yes. So we are going beyond Hartree-Fock means that I have bonding and anti-bonding orbitals with different weights. But as I told you, we are going to optimize the wave function, not in this MO basis, but in the atomic basis. So once we're going to optimize the wave function in our code, in TurboRVB code, we're going to take these ansatz here, and we're going to optimize these lambdas to minimize the variational energy. So the coefficients we're going to optimize are not those in front of the MO orbitals, but those in front of the atomic basis set. Okay, and the MO orbitals are just obtained after diagonalizing the pairing function, the geminal, written and optimized in the atomic basis set. Of course, it's given the shape of these orbitals. It's, I mean, given the matrix lambda, you can now know the sort of you can express lambda I as a function of the matrix lambda here. Okay, but the starting point for us will be the atomic expansion. Okay, so yeah, in the particular solution of Higher London, in the Higher London solution, there are two MOs involved, so it's beyond that Fock, and the two coefficients lambda 1 and lambda 2 are given by this relation, and the first MO is the bonding orbital, the second one is an antibonding orbital. But again, I'd like to stress that we are not stick to bonding antibonding orbitals. We are much more general, okay? Because we are optimizing this in a full atomic complete basis set. Okay. So is it another question?
Yes.
We did not introduce correlation term in our expansion. We did because these, I mean, the fact that we have many terms in this expansion means that we formally have in the Slater determinant representation, we have a linear combination of Slater determinants. So, so that's another way of seeing correlation, because going beyond the first term means basically it's equivalent to expand the two electron wave function in terms of more than one Slater determinant. Okay. Yes, so for this two electron problem, the geminal expansion is formally exact. Okay, so I have a formally exact solution for the two electron problem. So what about the many electron? And I would stay with this sort of framework way of thinking, many pair problem. Okay, I dare to change the many electron into many pair notation. So what about the many pair problem? To address this many pair problem, we introduce another ingredient, okay, which is the Jastrow factor. Okay, so the Jastrow factor is used for two main reasons. The first one is more related to a one body physics. So the Jastrow factor in our wave function will fulfill cusp conditions, and you have seen cusp conditions with Claudia and Anthony. And the second reason to introduce the Jastrow factor is to deal with the many pair problem in a size consistent way. Okay, so we have we're going to introduce the many pair problem. I'm going to see the role played by the Jastrow factor in this situation. I'm going to take a bottle of water. Okay. So now the Jastrow factor. Jastrow factor, you have seen this, right, already? Yes. So it's a bosonic factor. So at variance with the pairing function is bosonic. So there is no sign change if you permute 2 electrons, and it's written and it's included in the wave function in this way. So it's so you get an extra factor which correlates the antisymmetric part. Okay, so you apply the Jastrow factor to our geminal expansion. Okay, so and so one of the reasons to introduce Jastrow factor is to fulfill cusp conditions. So cusp conditions are exact conditions for any eigenstate of the Hamiltonian, and we'd like to impose these conditions to our variational ansatz. Okay, and so in a nutshell, the cusp conditions are such that for electron-ion coalescence, so in the case an electron and ion are collapsing on the same position, if you expand around this collapsing point, you get this form here. So the ratio of the expanded wave function over the collapsed wave function is 1 minus z, which is the atomic number of the ion involved in the collapse, times the distance between the electron and the ion which are collapsing. And in the case of the electron-electron coalescence, so in the case of 2 electrons are getting together on the same spot, the same point, the ratio between the wave function where you stretch a little bit the 2 electrons farther apart, divided by the wave function where the 2 electrons are sitting on the same position, it's 1 plus 1/2 the distance between the 2 electrons. So that's the asymptotic, I mean, the linear expansion around the collapsing points for two electron-electron collapse and electron-ion collapse. So this is an exact property, which is basically due to the need of compensating the Coulomb divergence with the kinetic contribution. Okay, so that's the idea of the cusp condition. So the local energy of the wave function could behave very badly around at these collapsing points because the Coulomb potential diverges. It's a very nasty potential, Coulomb potential. And so you should compensate this divergence by an equal divergence, but with opposite sign coming from the kinetic term. And to make this happen, you should have these cusp conditions in the shape of the wave function. Okay, so around the collapsing point, you have this sort of behavior, right? The cusp behavior. Okay, so now we impose this cusp condition to the Jastrow factor using this form for the Jastrow factor. So first of all, it's a product of the electron-ion contribution times J1 times the factor for the electron-electron contribution. So electron-ion, you sum both over ions and electrons, and you have this shape here. So it's an exponential. It's an exponential of a pairwise function involving electrons and ions, 1 electron, 1 ion at a time. And the shape of this U function, it's radial, okay, and it's given by this. This is one of the possible forms we can use. It's a Padet form weighted by the atomic number of the atom involved in this pair. So this Padet, if you expand this, so how can you see that this form fulfills these cusp conditions? Because if you expand now this Padet, the exponential of the Padet for small r minus capital R, you get exactly this term here. The leading term will be this one. Okay, yes, there is a question on the chat. A and B are always positive. Yeah. So yeah. First of all, there is a question about also the electron-electron part. So let me finish first, and then I take this question. So that's the electron-ion, and then there is the electron-electron part, which is also developed as PADE. Okay, and the same strategy, right? It's this one, and so the small. If you expand this at small r, you'll get the leading term, which is 1/2 the distance r. So now the PADE is more than that. I mean, it's more complicated. You have also this A and B as variational parameters, and A and B basically control the long-range behavior of this function. So A and B are meant to interpolate between the short-range behavior dominated by the cusp conditions to the long-range behavior, which is basically a constant. Okay, this constant is Zi over A for the electron-ion term, and it's 1/2b for the electron term. Okay, so so basically you avoid the blow up of the Jastrow factor in this way, because if you take just the leading term, this will be r/2 for a small r. And if you keep going with, in this way for the full range, this will explode at large distance. So the PADE is able to control, to reshape the form, the asymptotic value of this correlation, such that the asymptotic value is a constant, which is well behaved, also numerically speaking. And this B and A tune the transition between these two regimes, a regime where the function is constant at long range, and where we function as the cusp behavior at the short range. Yes, it's possible to use 3-body and 4-body, and yes, so it's a product. It's a product of. I mean, so there are different strategies to include the 3-body terms. The one used by Claudio and Anthony is to use a product of PADE functions to include higher order terms. We're going to use a different form. I'm going to explain you what's our strategy. Okay. So what was the question again? A, B? Yes. So if they're negative, no, because why is no? Because we'd like to have, as I just mentioned, we'd like to have divergence of the argument of the exponential. And so if B now is negative, so they should be positive, definitely. Okay, A and B should be positive, definitely. If A and B are negative, you would get the blow up of the function at some distance, either electron distance or electron distance. We'd like to avoid this blow up, and that's exactly the reason why we introduce A and B, to avoid the blow up at asymptotic behavior at large range, a long range. So we don't like to have any blow up at intermediate range, and so that's why A and B should be positive definite. Okay, all right. So now let's plug J1, J2, the Jastrow, into our geminal, our 2-electron function, and so you see that J1 and J2 act as bosonic, symmetric functions, which basically augment G. So G is augmented by the Jastrow factor. So G in the singlet framework is a symmetric function, bosonic function, and J1 and J2 are also symmetric functions. So these X, I recall that X are collective values. Okay, so X are R1, R2, X is R1, R2. Okay. Yeah, so I basically so what is the role now? You can see the role here now of the Jastrow for the geminal. The role of the Jastrow for the geminal is to augment the expansion of the geminal itself. Okay, with the form which is not a linear expansion in atomic orbitals, but it's starting more because it's an exponential of a pair function. So it's an augmented space. It's an augmented space which is clever because this augmentation is able to fulfill the cusp conditions. Okay, and so it's an augment. So it helps it reduces a lot, drastically, the length of this expansion. Okay, so this expansion, in principle, is meant to take these cusp conditions, to include these cusp conditions. So this will cost many terms. It will cost the inclusion of many terms. Instead, with a Jastrow, which includes in a clever way the cusp conditions, you reduce a lot. You converge much faster in the two-body basis set. So that's the first usefulness of the Jastrow factor. So it helps to drastically reduce the convergence of the pair function in the two-body basis set. And so, and Jastrow correlates the electrons because it takes into account the relative weight between the electrons, because it depends explicitly on the electron-electron distance. Okay, so it correlates. So that's why we call Jastrow correlated geminal. Okay, Jastrow correlates electrons. It helps in speeding up the convergence of the geminal, and the full wave function, Jastrow times geminal, is called Jastrow correlated geminal wave function. Okay, now let's go to the many pair situation. So this was for a single pair. Let's go to the many pair situation. So we'd like to build a fully antisymmetric wave function. This is the idea. We'd like to build a fully antisymmetric wave function based on the elementary brick of the most generic geminal wave function. Okay, I would say a most generic two-spin one-half wave function. Okay, so this, as we have seen, right, for the H2. So this will be the H2 wave function. This should be antisymmetric. Okay, but I don't like to restrict myself to a spin singlet. Okay, so in this situation, I allow this G. So this G now, sorry, it's a sort of misleading notation. This G is not the special part we have seen so far. Okay, so this G now is not the special part. This G is the full two-body wave function with spinors, spin plus special part. Okay, sorry, that's kind of misleading here. So again, G in this, from now on, G is not the special part, but is the full spinor two-body wave function, okay? Which includes both the spin sector and the spatial sector. And I don't like to stick on the singlet symmetry for the spin. I'd like to be as generic as possible. So I'd like to include also triplet components. Okay. The only requirement is that this spinor two-body wave function is antisymmetric. It's the only requirement, but it can break the spin symmetry. Okay. Now, for me, that's elementary brick upon which I'm going to construct the many pair wave function. And now I'm going to take, if I assume that I have enough pairs, okay, I have enough pairs, I'm going to construct now the fermionic wave function for these enough pairs based on the elementary brick G. So I should antisymmetrize the product of n-half terms, each one made of this pairing function, this geminal function, and the antisymmetrized product of this geminal function is nothing else than a Pfaffian. Okay, so if I write this properly, I realize that that's a Pfaffian of the matrix, of the skew symmetric matrix, that's the antisymmetric matrix Mij, where Mij is written as G R I. Sorry, that's so it should be Ri, not R1. Ri Rj. Okay, Ri sigma I, Rj sigma j. And the Pfaffian, again, as usual, this term will involve n-half factorial terms. So it will be an exponentially large number of terms, but thanks to the linear algebra, I can compute the Pfaffian in n cube with n cube operations, as for the Slater determinant. Okay, so it's again a huge gain in terms of computational cost. Okay, so just to summarize, so the Pfaffian arises from the idea of constructing a many-body wave function using as elementary brick a pair function, which is antisymmetric. If I apply the antisymmetrization operator to the product of pair functions, I get a Pfaffian, and not a zeta determinant. Now, in which cases the Pfaffian reduces to a zeta determinant? What are the cases where, as I told you, my pair function here is not restricted at a given spin sector, can be developed on both singlet and triplet spin sectors, okay? So in the case my pair function is a singlet, okay, if I take this brick as pure singlet, I apply the Pfaffian, and I realize that by Pfaffian application, I get the zeta determinant. So the Pfaffian is formally equivalent to a Slater determinant in the case my brick is a pure singlet. If this is also true if my brick is a pure singlet plus the pure triplet state with S equals 0. Okay, so if I have, this is my lab. No, it's not my mobile. So if my brick is made of the singlet plus the triplet with SZ component, that's also true that the Pfaffian is equal to the determinant. Why is that? Because the Pfaffian is this one, right? By definition, the Pfaffian is this object. I sum over all permutations of n terms of n particles, and you see that I should permute the permutation operator acts on all n indices here, and G is the pair function. So this pair function can be written in terms of this matrix here, where now the first the diagonal blocks are the up and down terms, and the off diagonal blocks are the up down and down up. Okay, so this matrix is this Gij. Okay, so Gij, right, is this matrix here, and now the first half is for I running over the up spins, and the second half is for I running over the down spins, and J here, that's for the columns. For the rows, the same. The rows, the first half is running over the up spin, and the second half is running on the down spin. So I have now up terms, down terms, up down, and down up. Okay. So if I have these contributions here, I don't have up or nor down. Okay, in these cases. So in these cases, the up and down are 0. And so if I take the Pfaffian of this is equivalent to the determinant of the single block. Okay, so in this case, the Pfaffian reduces to a Slater determinant of the pairing function. Okay. Okay. So again, Z determinant of the pairing function. So this includes correlations already. So it's not, sorry, I was wrong. So it's not the Slater, it's a determinant. Okay? It's not the Slater determinant. is the determinant, not the Slater. It's not the Slater. This is the determinant of the pairing function. It's not the Slater determinant. That's a very important mistake I made here. Okay, it's a fundamental mistake. That's exactly the point. It's the determinant of the pairing function, which includes correlation. It's not the Slater determinant. Okay. All right. Sorry about that. Okay. So now, if this G includes also triplet terms, this relation doesn't hold any longer. So the Pfaffian is truly providing something new. Okay, so it's really it goes beyond the determinant of a geminal. Okay, as soon as I have triplet correlations. Okay. All right. In this case, the Pfaffian is unavoidable. So let me summarize what we got so far. So we've been able to provide an ansatz for the full many-body problem, the ab initio Hamiltonian, given by the Jastrov times the Pfaffian of a pairing function. Okay, that's our ansatz, and we're going to play with it. Okay, and that's a very general form. It's very general with function form, and it can include correlations in many ways. Okay, so you have a quite flexible variational ansatz. There is a question.
How to include exchange in parallel case in Pfaffian?
How to include exchange? Yes. So I would say that the exchange in the parallel case is included naturally when I take the full antisymmetrization. Okay, so so if I go back to the Pfaffian form, so in the case of parallel. So what does it mean? I have just parallel contributions. So I have these now. These off-diagonal blocks are 0. It's the other way around, right? So these off-diagonal blocks are 0, and I have just parallel contributions. So this block is filled, and that block is filled as well, or just one of them. Okay. So, but the Pfaffian still acts on this block here, and I get the all permutations, all permutation in the parallel spin sector as well. I close this, or
Yes. Also the other one.
okay. Okay, let's move on. You don't know if you answered the question or not. I mean, if it was clear,
Yeah.
Okay.
Yes.
Okay. All right. So yes. So we've been able to. I mean, that's the idea, right? That's our framework. So we'd like to deal with this framework, which is very flexible and includes correlation in many ways. So okay. Now, just a side remark about, now it's a question also we got about many-body Jastrow factors. So in TurboRVB, we develop the Jastrow factor not only based on these Padet contributions, these EU, EE, and UEI are Padet contributions, but also developing the Jastrow factor in terms of this two-body basis set, the product of one-body orbitals. Okay, and so that's basically a very similar way of as expanding the geminal G, the special part of the geminal, but that's exponential. You take the exponential of this, right? And Jastrow, the Jastrow is the exponential of U. Okay, so it's an augmented way of expanding the geminal because you take the exponential of this, and this, what is the physical meaning of this? So if you take the Jastrow factor, the exponential of this term here, you correlate what? You correlate for body. Because you correlate, because now, again, phi I A, it's a localized basis set. So it depends on two indices, the electron, the state and the center, okay? And on the distance between the electron and the ion. So you correlate here for body because you have electron ion and electron ion. So you go beyond this homogeneous term is two body because it depends only on the distance between two electrons. But here, this function is more complicated. It's non-homogeneous, inhomogeneous, and depends on four centers, like two electronic positions and two ionic positions. So you have a very large number of parameters here, see? So because in the many body system with many pairs, you have many centers. You'd like to expand the wave function properly with the many elements in the basis set, and you do this for both geminal and Jastrow factor. So you have all these matrices here. Okay, you have all these matrices, and these matrices are have n square entries, and so this grows with the system size. Okay. Both in system size and also basis set size. So you have a lot of parameters to optimize, and this will be the subject also the second part of my lecture about the optimization. So we're going to show how to optimize this very large number of parameters. Oh, so it's very bad this. Now let's go to the second reason why we should include the Jastrow factor. So we have seen the Jastrow factor is very helpful to encode the cusp conditions, to fulfill cusp conditions, but there is another reason. Okay, I mentioned two reasons before: cusp conditions and also dealing with many pair systems. So now let's take the system of H2 gas. So we have a gas of dimers. We have many dimers together. Okay, and you take just a single dimer, single H2. Single H2, we have, as we have seen in the most general way, you have many terms in the pairing function, but the most important terms are the bonding and anti-bonding, okay? And the anti-bonding are weighted a little bit less than the Heitler-Rondo solution. So you still have ionic terms. So that's basically it's a good variational form for our H2, okay? So you with this you control the ionic terms. But you have two MO orbitals, okay? You have two molecular orbitals. The bonding and anti-bonding, gerade and gerade. So these two MO orbitals can accommodate 4 electrons. Okay, up, down, and up, down. Okay, to up, to down. It's the same thing. So you can accommodate, in principle, 4 electrons, not just 2. Okay, so if you have just a dimer, the number is 2 because you have a dimer. But if you have a gas, some pair living eventually on another dimer can, in the wave function can be transferred to the pair of reference. Okay, this is the pair of reference, for instance. Okay, so you can have strong charge fluctuations. So that's a major drawback of the geminal without Jastrow correlation. If you put the product of geminals, so the AGP was indeed proposed by chemists in the 80s already, okay? So it was an answer, it's already known by chemists in the 80s, but they didn't put the Jastrow factor. And if you take a many pair problem, not just H2, a many, because H2 is exact. Huh? If you take a many pair problem, you have a strong charge fluctuations due to the fact that a single dimer can accommodate more than one pair, because you have the space is available for accommodating other pairs, okay, due to the expansion of the geminal. And if you don't if you don't cure this issue, the AGP is another major failure. Okay, so the two-body problem is exact, but the many pair problem is badly wrong. So that's the second reason why you include Jastrow factor. Jastrow factor can control charge fluctuations. Okay, you can write the Jastrow factor in a way that you can control the number of electrons sitting on a given pair. Okay, and you can prevent more than 2 electrons sitting on the same pair. All right, and that's basically the second reason why the Jastrow factor is fundamental. Okay. Now, the combination of the Jastrow factor and the geminal function has been known also by condensed matter physicists. So while chemists, they proposed just the AGP as an ansatz, physicists had already in mind the Gutzwiller projector, okay, in the same ages, in the 80s. So the Gutzwiller projector is exactly just a simplified Jastrow factor, which cares, if you like, only about the occupancies, okay, and it avoids double occupancies of a single site, for instance, okay. So the combination of Gutzwiller and BCS, Bardeen-Cooper-Schiffer wave function, was basically the recipe proposed by Anderson to describe superconductivity in the famous science paper in '82. Okay. Now you can prove that AGP, so our geminal in the singlet spin sector, our geminal in the singlet spin sector is the particle conserving version of the BCS ansatz. So the BCS ansatz is not particle conserving, so it works in the grand canonical ensemble. But if you restrict this BCS into a fixed number of electrons, you recover AGP. So you see that the Jastrow correlated AGP was already used by physicists in the 80s, and they proposed this to describe superconductivity. And the theory also was known by chemists. But chemists, they were using sort of graphs to represent this theory, not wave functions. So they didn't have because they don't like Jastrow factors. I don't know why. I know why, because Jastrow, I mean, that's the reason why we do quantum Monte Carlo, basically. Okay, so we do quantum Monte Carlo with this wave function because we have the Jastrow factor, and Jastrow factor makes basically the calculation of any expectation value impossible, but within a stochastic framework. Okay. So anyway, the chemists, they had the idea of having pair functions not overlapping, I mean, without double occupancies. And that's also what's called a resonating valence bond. So RVB exists on both sides of the world, basically, both the chemist and the physicist. Oh, well, come on. Sorry about that. There's some chemists complaining, maybe. Okay. Anyway, so and so yes. So what is the idea? The idea is that you have basically the superposition of singlets. Okay. So I mean, let's stay in the singlet sector. Okay. In the singlet sector. So in the singlet sector, the covalent bond. I mean, the description is the traditional description of covalent bond is a singlet. Okay. Is a singlet joining two nuclei, and that's exactly this form here, right? So the singlet and joining two nuclei, so A and B, okay? And that's our geminal in the singlet sector pairing function. And if you take the superposition of all these states, you get the RVB state. So let's take the benzene case. The benzene is the textbook example to illustrate the RVB theory. So you have basically the chemical bond is mainly driven by the pz orbitals. You have six valence electrons in 6 sites, and so you should accommodate these 6 electrons. And you can accommodate the 6 electrons with these different configurations. Okay, so those are the RVB diagrams, where now the double bond here means that you have the binding, the covalent bond made by the pz electrons, the pi electrons. Okay, and you see that in this graphical representation of the theory, 2 bonds having overlapping on the same site are forbidden. Okay, so you should forbid, you should avoid the touch of 2 bonds, basically. Okay, they should be all disconnected. So there is sort of frustration of the chemical bond here, and you can draw many diagrams. Okay, so so you should draw all possible diagrams having 3 covalent bonds, which accommodate 6 electrons, two for each bond, not overlapping. Those are the rules of the game. And so you can draw many diagrams. Those are the diagrams in the benzene diagram. Of course, if you have aromatic compounds, you have an exponentially growing number of diagrams with a number of sites. Okay, if you take the RVB papers, they draw all these diagrams and compute the energy the energy gain of all these resonances and so forth. So all this game is played automatically by the just correlated Gemini function. Okay, this is played automatically. You don't have to draw anything. So you just optimize the variational parameters, and the optimization variational parameters will give you the strength of each of the coefficients of each diagram automatically. Okay. And now what is so you can see now you can understand physically the meaning of the different sectors of the wave function. So the geminal, the pairing is the one developed, on the full system. Okay, because it's the geminal is a function which is delocalized. Okay, which is occupied by 2 electrons at a time. So you have a product of geminals which accommodate 2 electrons for each term, and these electrons, why they don't overlap? Because there is a Jastrow factor. The Jastrow factor kills situations where you have these links are overlapping, or even worse. You can imagine of drawing 3 lines parallel. Huh? That's I mean, in the AGP, in the AGP without Jastrow, drawing 3 parallel lines is a possible is allowed configuration. This will be will have huge variational energy, because you have not just double occupancy, but you have triple occupancy. Huh? So the Jastrow will prevent all these nasty charge fluctuations, still allowing the geminal to exploit resonances between different configurations. Okay, so I think I just I made the story messing up all these the sequence of these slides, but anyway, yes. So I think you got the idea. And now let's take a cartoon picture of the RVB or JGP wave function. So you should imagine of having many of these configurations where from time to time, I mean, you have basically each configuration is made of pairs of electrons linking 2 sites. Okay, and basically that's this is the picture also proposed by Anderson to describe superconductivity in the cuprates, where now the superconductivity, according to Anderson, is takes place when you have a charge defect. You have a hole, And so then the Hall can propagate in this sea of pairs, okay? And when you have these pair condensate, because the pairs, the singlet pairs, are bosons, so they can condensate, and this condensation of pairs plus the charge freedom of a single Hall propagating or more Hall propagating the compound, this will basically provide you the superconducting behavior of the Halls in the cuprates. But okay, in the case of chemical systems, this is many body wave function with resonances involving, if you like, in a quantum picture, you have a dynamical formation and breaking of the chemical bonds. So you have a sort of a soup of bonds, of singlets forming and breaking. A distance between two sides in which resonance bond is possible. Dewar double bonds are not equal. All these three are equivalent, no? Why they are saying that they're not equal? They're equivalent. This is singlet. All these are singlet. No, it's not triplet. Okay. But in the Pfaffian we have also triplet correlations. But the RVB, strictly speaking, is for singlets. Although I mean the Pfaffian is generalization of the RVB theory also for triplet correlations. Okay, so all right. Now that's a good question because it allows me to introduce another concept which is typical of the Pfaffian wave function, which is the spin fluctuations. So we are talking about charge fluctuations due to the fact that these pairs can sort of fluctuate, can form, break, and be controlled by just a factor, but we have also spin fluctuations. Okay, so now what about spin fluctuations within a singlet? So that's a question actually that I've asked at the right time. What about spin fluctuations in the singlet sector? So if you have a spin fluctuation, let me rephrase the question. Is it possible to have spin fluctuations in the singlet sector only? And the answer is no. And the reason is the following. So, that's basically one of the terms of the singlet, right? Up, down, and then you have minus down, up here. So if you apply the Jastrow factor on this, the Jastrow factor, even a spin one, depending on the spin, the Jastrow factor will be written. The quantization axis of the Jastrow factor will be the z axis. Okay, so up or down, right? Spin up or spin down. When we talk about spin up or spin down electrons, the spin up or spin down, it's up and down with respect to the direction given with respect to the quantization axis. And you can choose whatever you like, but the convention is we take z as quantization axis of the spin. Okay. Now the Jastrow factor written in the same quantization axis as the singlet in the geminal won't flip the spin. Okay, it's not able to split the spin. So the Jastrow factor doesn't flip the spin. Jastrow factor projects basically some states, but doesn't flip the spin. There is no spin flip operator in Jastrow factor. Okay, the Jastrow factor is basically density operator, so it doesn't flip the spin. So you cannot get spin fluctuations if you are in the singlet sector. Okay. Now imagine that we are dealing with the most general geminal. So not only the singlet sector, but we also allow for the triplet components without any spin symmetry imposed. So if we do that, we can write a pair of spins now starting from a pair lying on the pointing on the y-axis. So we can flip the spin of the pair such that each spin is oriented not along the z-axis but along the x or y-axis. Okay, so if we rotate the spin such that the spin is no longer oriented on the z-axis but is oriented either on x or y, in terms of spinors, this implies that I should mix the spin up and spin down components. Okay, so if I'd like to have a spin oriented on the x or y axis, this spin should be an eigenstate of the Pauli matrix, either x or y. Okay, and the Pauli matrix either x or y involves off-diagonal terms, flipping the spin direction, and so an eigenstate of the x or y is in a combination of the up sector and the down sector with proper coefficients. Okay. So now, if I make the product of these spinors, which are linear combination of up and down, I get up up, down down, down up, down up, up down. Okay, that's the idea. So if I start from a pair where the spin is aligned on the x or y axis, whatever plays the game, I get a pair which is a linear combination of up down, down up, up up, down down. Okay, and you can start seeing the light in the tunnel, because you can start generating terms. Okay, new terms. You can start generating. In particular, you have the up down, and then you have the flipped contribution down up, generated by this configuration. The problem is that you have also up up and down down, and if you'd like to stay in the singlet frame, so this frame will be a bad frame because it will be strongly spin contaminated. We have a strong spin contamination because this won't be an eigenstate either of s equals 0 or s equals 1. It will be strongly spin contaminated. So we'd like to preserve spin pureness. I don't know. So to preserve to avoid spin contamination, we applied the spin Jastrow factor. Okay, which kills the up and down contributions. Now the spin Jastrow factor can kill contributions because it's a density, and it will kill two densities having up or down occupations. So this can be done by the Jastrow factor. So you can see now that the application of the Jastrow factor on a rotated geminal allows for spin fluctuations, because now I can go from I have a linear combination of up down and down up. This is exactly spin fluctuating term. Okay, so 10 minutes, yes. This is good for us. I mean, it's a very nice property. So you see that another feature of dealing with Pfaffians, because again, I'm going to recall you that only Pfaffian will allow triplet correlations. So only within the Pfaffian I can write this term here. Okay, so I need Pfaffian to get this. Okay, so the Pfaffian combined with the Jastrow factor, the spin Jastrow factor, will allow for spin fluctuations within the spin singlet sector. Okay. There is a question.
Oh, yes. But the net moment
will be along the axis only in the right side. In the left, okay, but the net moment will be along the z-axis only in the right side, but in left spin moment in xy plane. I mean, no, so that was just a cartoon, I mean, just was a sort of cartoon picture to understand what's going on. So I won't start with this guy here. So I know by, I mean, formally that this guy is nothing else than a linear combination of up, down, down, up, and down, down. So I start from a linear combination, I start from this guy here, and I know how to write a generic form for this guy. Okay, so a generic form for this guy is nothing else than the compact way of expressing this is this one. Okay, but my brick is not that one. My brick is the quantization along the z-axis anyway. But a quantization which will include not only up, down, and down, up, but also up, and down, down. So the meaning of including up, and down, down is to have a generic orientation in the spin of the pair, the spin of electrons forming the pair. Okay, so it's another way of seeing things. Okay, the fact that I have a generic expansion which breaks the spin symmetry can be seen by applying the Pauli matrices, can be seen as a pair oriented in a generic direction in the spin space. Okay? Yes.
Rotation on this state, or how
you can go from so for instance, if you apply the yes, I think you can. So if you apply the Pauli matrices to this state, I mean, for instance, I mean, if you apply SZ, we will say on this state, right? If you apply sigma x, sigma y, you'll flip. So, I mean, I don't know if I don't understand the question. So you how to yeah. So yeah, right. So the operator which rotates the spin is a linear combination of the Pauli matrices, right? It's the So you can write it as a, it's written in the complete space of the 2x2 matrices, which is a combination, the identity plus you can write any rotation in the 2x2 spins SU2. No? Yes. But anyway, so the point is that we are stick to the Z quantization axis. Okay, so everything is written. I mean, the Gemini is written in this space here, never in that one. Okay, so then formally you can go from this one to that one, but it's a formal equivalence. Okay, just to tell you that, I mean, to get spin fluctuations, you should apply a Jastrow factor to a state which is formally a spin state whose spin directions are not oriented along the z-axis, but oriented on either on x and y-axis, then you have spin fluctuations. And this is allowed, that's the major point, this is allowed by the spin Jastrow factor applied to our geminal wave function written in the most general form. I mean, the Pfaffian. Jastrow applied to the Pfaffian. Okay? So this has been also proposed as the solution, the Heisenberg model for large spin by Sandro in the early 1997, okay, late 90s, but early for our. So it was an early work by Sandro where he applied this on lattice models. Okay. Anyway, so now I have still 5 minutes to go. Okay. Okay, so now the last 5 minutes to show you a very nice application Sandro did last year using these Jastrow correlated Pfaffians to study the C2 dimer. Okay, and so the question is, what is the chemical, what is the nature of the chemical bond in the C2? C2. So so C2 is sort of very peculiar and also pathological in some sense. One of the weird things of C2 is that if you now if you compute the S square operator on the two fragments. I mean, on two C fragments. You see that the value of the S-square operator on each of the two fragments has a value which is very large, has a value which is as large as the isolated fragment. Okay, and that's very strange. It's not usual at all, because usually when you start from a spin polarized molecule, spin polarized atom, and you form a molecule out of this spin polarized atom, as soon as you form the chemical bond, the local moment is screened. The local moment of the atom forming the molecule is screened. You see, it loses the original spin moment it had in the isolated limit. In the C2, this doesn't happen. So that's a comparison between C2 and N2. N2 is the blue open triangles, and C2, the C2 is the red open circles. And you see that basically the local moment of the C atom in the C2 molecule basically has the same value as the spin moment of the isolated carbon. And that's the first thing, which is this local moment which is unscreened. The second thing is that the C2 bond is very strong. Is very strong, despite being a double bond in the standard valence bond theory. Despite being a double bond, is very strong. Is one of the strongest double bond in nature. Okay, and why is so strong? That's another question. So to explain this, the strength of the C2 bond, there was a theory developed in 2012, where now the hypothesis is that instead of dealing with the double bond, you have a quadruple bond. So the C2 in this framework is not a double bond, as suggested by valence bond theory, involving the pi orbitals, but it's a quadruple bond because you sort of deplete the Angerade sigma orbital, the two sigma orbital anti-bonding, and you populate the 3 sigma Gerade bonding orbitals. Okay, so you fluctuate between these two. I mean, that's RVB occupied. So you fluctuate between these two occupancies, and you deplete the anti-bonding 2 sigma Angerade, and you populate the bonding 3 sigma Gerade. So this, in principle, is an allowed state, and eventually this paper showed that energetically that does make sense, and this could explain the strength of C2. But it doesn't explain why the bond length of C2 is longer than the bond length of the 2 carbon atoms in, so if you kill this comment, please, of acetylene. Okay, so okay, what is the comment here?
But energy
get increases
for the right one, probably.
Yeah, maybe I don't know. So I don't know if you get. Okay, so the point as far as in the right. And so, I mean, that's a question, right? Whether this is favorable or not. I mean, according to this paper, it's not that bad. Otherwise, the theory wouldn't apply. Anyway, so the question is that in the acetylene, you have the length. The length is shorter, and so there is a sort of mismatch. So you have apparently energetically stronger binding energy in principle, but we have a longer bond length. So there is an incoherence. And so Sandro applied the Jastrow-Pfaffian on this C2. And what he discovered is that, first of all, optimizing this wave function at the variational level, Jastrow times Pfaffian, with the Pfaffian now includes not only singlet, but also triplet correlations. So it's a really generic, the most general pairing function. So it allows spin fluctuations. By optimizing this, he found that, first of all, the spin contamination is very low. So the spin Jastrow factor cures the spin contamination you should have in this case here, right? Because it's fully spin contaminated. So Jastrow factor is really able to play this game very well. It recovers a singlet. And so it's a good, sign. It's a sort of it's a sanity check for the wave function. This is a sanity check for the wave function. So the Jastrow factor recovers the spin singlet nature. Okay, it means that it's very well optimized. It acts as it should. And secondly, the population of the orbitals, of the M orbitals, is not the one of the quadruple bond, because you have a strong population of the anti-bonding 2 sigma Angerade. So it's not empty. It's fully populated, but you have a strong contamination of the one body MO orbitals of 2 sigma U and 3 sigma J. So it means that this contamination is the one which allows for spin fluctuations, because it's the one which allows the mixing, the creation of these terms here. So these terms are created when you start from an orbital which has both up and down components. Okay, so the spin contamination of the one body molecular orbitals is a signature that the wave function wanna play this game, wanna generate spin triplet correlations, and so which are present in the Pfaffian, and these are the responsible for spin fluctuations. So the interpretation is that the extra binding energy is due to spin fluctuations, and this explains also why the bond length is larger with respect to the acetylene, because we are still dealing with a double bond, so it's weaker than a triple bond, but the extra energy gain is due to the spin fluctuations, which are strong. And with this, I conclude this. So if you have any questions, you can take a break. Can you conclude spin contamination C2? So I can repeat the story of spin contamination. So if you take the general Pfaffian, right? The general Pfaffian breaks spin symmetry, okay? Because it's antisymmetrization operator on a geminal, which is antisymmetric, which is fermion antisymmetric, but it's not. It doesn't belong to any spin sector. It's a linear expansion over different spin sectors. Now, an eigenstate of the C2 Hamiltonian should fulfill the spin symmetry. Okay, so it must belong to one of the spin sectors. Okay, in particular the singlet spin sector. So now we can use an ansatz which break the spin symmetry, but by optimizing, so if the optimization works, at the end of the story, at the end of the optimization, I should kill the terms which pollute the spin of the wave function. I should get, if the optimization works well, I should get a state which is as close as possible to a pure spin state. Now, in the Pfaffian, I'd like to still have spin contamination in the Pfaffian, because I'd like to have the physical spin fluctuations. But the Jastrow times the Pfaffian should kill spin contamination. And this is exactly what the Jastrow does in this case. So the Jastrow allows, combined with the Pfaffian, allows for spin fluctuations while preserving the spin symmetry of the singlet in a very close, in a very good way, because the spin contamination is very, very mild. So the S square is basically 0. So it belongs to it nearly belongs, almost exactly belongs to the singlet sector. Okay? I think we can stop here. Yes, let's close this. Yeah. Okay, yes.
So there's nothing in the next block, so we could say that this is somehow finished. Okay.
Yeah, sure.
Okay,
That's
okay,
exactly what I'd like to do, because
Okay.
then we're talking about
Yes,
optimization.
Yes, yes,
Yeah.
yes. Okay.
No, it's perfect
No,
time.
okay.
Yeah, yeah. Hmm.
Let's say if it's not comfortable for you to really ask the answer the question, which is, let's say, somehow pop up. So let's say
No,
we
it's
could
okay.
kill
It's
it
okay.
also.
No, it's okay. It's okay. No, but that one was just hiding
Let's say the Claudia was able to react like it.
It was Claudia asking. Who was asking?
No.
Ah, okay.
When it was the Claudia speaking, then
Mm.
also this guy was trying to ask one question.
okay.
Like when it was just said, if somebody was to ask, please come.
Yeah.
He was to write something on the blackboard. So
Yeah,
the
no,
guy
no.
asked why you don't see what he's wrote. So so I just would say, you could say, it's not comfortable. You could kill this and okay. Yes. Yes. Such a format is not, let's say, completely easily count everything from online and also from. So I just think even it's fine. See that everybody has to make the presentation and somehow it need to be like
It's nice that we have some reactions also from somebody there, yes. Yeah.
But like it's ourselves really. There is somebody who is monitoring.
So can I admit this guy?
Yes.
Or not? Yes.
I think yes. I think yes. Because there's also Julia, I think. So Julia is of course. So
And there is
maybe she
also
also take lunch, right?
So I don't was what was precious about this part, even the phone of the speaker. You know what we must the construction meeting in the US. And really my doctor was a tornado. meeting the place. So that we had a power outage and it was just like a confusion slide. Power outage. You know, everyone, waiting on the end. So then the power came back. Power came back after 10 minutes. Then I experienced many unfortunate events during the anyway. Usually out the door. That was in a good season.
questo è un po' di base per la casa, ma solo per me fa mi piace. Allora, vedo c'è uscire scala. Dopo ogni candidate sistema di ciò, la considera che ho visto chiamato alle pratiche produttive e viviamo nei 5 per killing factor se derivate che vedono si ha a si chiede come meccanismo di base per mantenere sì, del principio di parte che io potessi accontentare lo determinante tu di la produzione a seguire con i che possa dare in che è importante possiate dare di braccia non potete arrivare non devi fuori già se tu ci prendo anche che dici finisce l'italiano io avevo fatto una certezza che tanto malo che basta sapere tu chiamate quasi fonti a di sempre riuscito per fare farlo di vai sapere anche per anche una pratica ma che del fatto di fare ogni riesce ogni ieri questo è prima che ordinare la cosa che anche molti compitati e stati assolutamente è stato visto bene a finire la modo di
So, Ivan, I have one hour. Okay, so I have usually 5 hours. Okay.
Hey, microphone.
Yes. Does it work now? It's recording?
Yes.
Can you hear me?
Okay, great.
Okay. Oops.
Yes, it's green.
Is it working? Okay. Yes, I
It
think
must
so.
be
Yeah, okay.
blinking by yes, it's blinking. This is
Okay, good, good. Okay. So, okay, let's resume, and we'll start with the second topic of this series of lectures. Is about which is about wave function optimization and ionic forces calculation. Okay, so we have seen that the wave function, the just correlated Pfaffian, is a beautiful wave function because can describe different physical situations, and in particular spin fluctuations and correlation due to resonance of low-lying energy states. But we have many parameters. Okay, so we should optimize both the Geminal matrix and also the Jastrow matrix. So we have a number of parameters which grows I would say quadratically and quadratically with the system size or the basis set size. To benefit from these variational ansatz, we should have a method which is able to optimize all these parameters. And that's the goal here. So you have now the wave function and alpha are the set of parameters to optimize. And we'd like to get the minimum of this of the energy of this wave function as a function of alpha. The wave function optimization in quantum Monte Carlo is a long story. It started since the beginning. Okay, so since the first study by Macmillan of helium-4. In that case, in the 1965, the wave function was very simple. Okay, it was a product of basically, the product of pairs. In that case, it's basically just a factor correlating the bosons, and we in that case we had two parameters, and Macmillan was able to optimize them, and also later till 2000. There are different studies published, for instance, on the TJ model or lattice models, where the wave functions were quite simple. They had quite a few parameters, and the idea at the time was to optimize this simple manifold by running variational calculations for each set of parameters. So for each set you have an energy, you change the value of the parameters, you run again a variation Monte Carlo, you get another energy, and you draw basically the energy landscape of these functional parameters on a grid. Okay, so you make a grid of these alpha parameters, and you fit the grid by a quadratic function, and you find the minimum in this variational space. So what is the drawback is that you should run a very accurate variational calculation for each set of parameters. So it's a huge number of entries, and each calculation is costly because you should run a full variation Monte Carlo. So we should find a way to make this search more clever and more efficient. Okay. So just a reminder, when you run self-consistent DFT calculations, you also optimize the implicit parameters. So you expand, for instance, if you run plane waves DFT, you'd like to get the coefficients of the G wave vectors. If you run DFT with a Gaussian basis set, you optimize the molecular orbitals. So you'd like to find the DFT coefficients in front of the atomic basis set. So also with deterministic method, the goal is to find the best functional or the best wave function which minimize the energy. The difference between deterministic and stochastic methods, in deterministic methods, you don't have noise. Okay, so I mean you can diagonalize them in Hamiltonian at machine precision, and so the minimum is numerically well defined, if you like. Now in quantum Monte Carlo, the big problem is the common presence of many parameters and quite sizable noise. Okay, so how to deal with the fact that we have many parameters and sizable noise. This is the question. So one solution was proposed by Cyrus Umrigar in 1998 and was based on the correlated sampling method. So the idea, again, is not to run independent variation of Monte Carlo for each parameter set, but to run just one Monte Carlo run and then exploit this run to optimize the wave function on different set of parameters. So different values for the parameters. So the idea of Cyrus was to basically exploit the weighting technique. So imagine that I draw a sample distributed according to psi alpha. So I run my quantum Monte Carlo calculation and I draw a sample distributed according to psi alpha. And then I know everything about this, the local energy, the expectation value of the Hamiltonian, and I'd like then to exploit the very same sample, not to evaluate the energy computed over this wave function, but the energy of a slightly different wave function, a modified wave function, where now the parameters alpha changed, the value changed from alpha to alpha prime. Okay, so by still using the former sample, okay, and so if the former sample was drawn according to this distribution, I can sort of formally rewrite the sample based on psi alpha prime using the ratio between psi alpha prime modulus square and the original psi alpha. Okay, so the ratio between the square modulus of psi alpha prime over psi alpha is analytically known. So I can compute it analytically and numerically. And these factors here are used to reweight the sample drawn according to the former wave function. And so now the energy of the wave function with alpha prime parameters is takes this expression, where at the numerator I have the original distribution pi, the one distributed according to all the set of parameters, times the local energy, which I know numerically, analytically computed for the alpha prime, times the correcting factors, Rx. And the same for the denominator. Also, the denominator should be corrected by their weighting factors. So their weighting factors are able to reshape to reweight the original sample such that it mimics the sample which is driven by the new set of parameters. Okay, and so now I got basically the important result that with just one sample I can span several values alpha prime. Of course, what is the drawback? The drawback is that if alpha prime is very far from alpha, then my weights start fluctuating wildly. So the fluctuation of these weights is exponential, goes as exponential the number of electrons. So if alpha prime is too far from alpha, the weights are too fluctuating, are too noisy, and the correction, the reweighting scheme doesn't work anymore. So I lose accuracy due to the exponential fluctuation of the weights as soon as I get away from the original parameters. So I mean, if you like, a solution of this problem is that if my alpha prime are too far from alpha, I should redraw a new sample So I should generate a new sample distributed according to the latest set of parameters, and then I should apply the reweighting to the new sample. So I should sort of iterate this as soon as I change alpha prime. So at the end of the story, I mean, for complex wave functions or for large number of electrons, I go back to, if you like, the previous situation of running independent Monte Carlo runs for each set of parameters, and because if you like, the shape, the landscape of these weights is too weak. They're too rough. It's too rough shape to basically smoothly connect different distributions. And this is even more true if you have large systems. Okay, but anyway, that was a major progress with respect to the previous dumb way of doing the optimization, because at least I could move in the parameter space with some direction which was computed based on the set of parameters alpha. So this if you like, this expression here, E alpha prime, allows me to compute the gradients of E with respect to alpha. So I can update alpha prime in a way which goes in the right direction to minimize the energy here. So so the reweighting was the first attempt, and again, that's the important point now is the possibility to compute energy derivatives. So I'd like to compute energy derivatives because I'd like to not to span the parameter space blindly, but I'd like to move in the parameter space along the directions which minimize the energy. So computing these derivatives is essential to move in the parameter space in an effective way, and by minimizing the number of iterations in this space. Now, the derivatives of the expectation value E with respect to alpha can be recast in this form here. So if you take this expression and you derive this with respect to alpha, you will get that these derivatives are equal to twice the covariance between the local energy and O, where now what is O? O is the logarithmic derivative of the wave function with respect to the parameter here. So what is the covariance? The covariance of EL and O is the average of EL times O minus average of EL times average of O. Okay, so yes, so I should evaluate not only the local energy, but also this local operator here, this OX, the logarithmic derivative of the wave function, and I should compute the average of the product of these two local operators, EL times O, minus the average of each of them. Okay. And so this can be done step by step. So at each step, I compute the energy derivatives, and I can use the steepest descent method. Okay, the steepest descent such that the new parameters are found by the knowledge of the energy gradients times this delta. Delta is the step function, value for the parameter change, and one can show that for small enough delta, the energy must go down. So I improve if I choose small enough delta. I certainly improve the variational energy, and the reason you can show easily the reason because if you expand, for instance, the energy at small delta alpha, you get the energy. Well, I can use the iPad maybe. So can you see the iPad then on the screen or not? Okay.
If you want.
All right. So yeah, so
There's a bug, so
okay, so we found is that alpha prime was equal to alpha plus delta, the derivative of the energy with respect to alpha, right? So actually minus, because we'd like to lower the energy. And so if now you expand, so you have E of alpha. If you expand now, let's say E of alpha prime, sorry. If you expand now this around alpha, you'll get the Taylor expansion at the first order, right? Plus delta alpha square order. And now if you plug now this delta alpha here, inside, you get that E of alpha prime is equal to E of alpha minus delta, the derivative of E with respect to alpha squared. Okay, and so plus order of delta alpha. So if this order, the remaining contribution of the Taylor expansion is negligible, you're sure that, and that's true for small enough delta, you're sure that to minimize the energy, because that's a positive term, okay? And so you, for sure, E of the alpha prime will be less than E of alpha for small enough delta. Okay, so the simple derivation that for small enough delta you'll minimize the energy in the steeper descent. Okay, so to stop it, yes, sorry. Okay, thank you. Ah, okay, sorry. Okay, great.
Just start.
All right. Okay. So, but as I'm bound by the delta alpha square term, I can find basically the optimal, for each iteration. I should find the optimal delta to minimize this the function. But usually you don't do this. I mean, you usually take a constant delta. Okay. So delta is kept constant along the full run. So if you take delta and set to a constant, so it doesn't depend on the iteration. Minimizing E of alpha is equivalent to minimize this cost function here, which is given by this, the first order expansion around alpha, so the Taylor expansion, the first order involving derivatives, plus the remaining term, which is cut off by 1 over 2 delta. Okay, and so what you can see here, of course, that for a small enough delta, this will be basically the bound factor for your minimization. What you can find here is that delta is the same for all k components. So k is the parameter index. So you have the same bound factor which is equally shared by all components, and you don't distinguish between fast and slow components. Okay, so you assume that all parameters are affected by the same curvature. What is the problem? Ah, sorry. Yes. Okay. Okay. And sorry, I'm sitting in the middle. I can move to maybe back to the. So now, what is is it the optimal thing to do? I mean, to keep this delta constant, or I mean, what is this? I mean, is it a way to improve steeper descent? So let's see how steeper descent works. Again, I take H2 as a test case. I have my wave function, right? We know the wave function now very well. And I take the simplest form. So the singlet, the geminal is a symmetric geminal. I have just the one body-to-body factor, which is homogeneous. So I have only the Padé factors. So from the Padé, I get two parameters, A and B. And from the geminal part, I get the lambda. It's just one lambda because the first lambda sets the normalization. I don't care. So this lambda tunes exactly the ionic contribution to the geminal. So if you like, interpolates between Hartree-Fock and Heiter-London. Okay. And I have optimized also the exponent. Okay. So usually something you don't do in quantum chemistry, but here we dare to do. So we have four parameters, right? So A and B for the Jastrow, one body, two body, lambda in the geminal, which interpolates between the physics of Hartree-Fock and Heiter-London. I mean, sort of try to find the best balance between covalent and ionic contributions. And the Z, which is the spread of my atomic basis set in the 1s component. Now I apply steeper descent in TurboRVB. So we're going to see some optimization today with Kozuke in the afternoon. So we're going to optimize the H2, right? So not only, but also. So now that's the optimization of the, you know, the energy goes down, it's optimized, it's minimized, and then you see the behavior of this optimization as function of this delta, the parameter step, the variation of the parameters at each iteration. So you see that if delta is too large, you have spikes, so you have instabilities. Okay, and if you decrease delta, you get a smoother convergence because, as we have proved, for small enough delta, you minimize always the energy. So here, I just like to point out that when we do the optimization, at each parameter step, we regenerate the sampling. So we don't do reweighting a la Umrigar, okay? So we really start from scratch a new quantum Monte Carlo sample, distributed according to the new wave function parameters alpha prime, okay? So because, as I told you, reweighting is unstable for large, it gets unstable for large systems. So we avoid the reweighting, we forget about Umrigar's approach of reweighting, and we really generate a new sample, a new quantum Monte Carlo sample for each and every new set of wave function parameters. So at each point here, it's a new sample generated. Okay, so now that's the energy, right? Now, if you look at the parameters, you realize that what you get is that there are some parameters that are very fast to optimize. They go, I mean, they move very fast, very rapidly, and then they reach the convergent value. Like, for instance, the Z the Gaussian exponent is very fast, is the fastest, then the Jastrow factor parameters A and B are also fast, but there is a very slow one, which is this lambda parameter in geminal, which tunes the ionic contribution in the pair, and that one is very, very slow, and you can see here that within the 1000 iteration range, you don't see, I mean, it seems to flat out, but I mean, if you keep going, you see that you need sort of 2 order of magnitudes larger number of iterations to get the convergence of this parameter here. So that's very inefficient, right? Because despite the fact that the energy looks quite well converged, right? Here, so after 100 iteration, you'd say, okay, I mean, more or less. But after 100 iteration, you see that there are parameters still moving, because there are parameters for which the local energy is weakly dependent. Okay, so but still, to get, if you like, the physics, because you know this lambda really tells you about the physics of the pair, right? So how I mean what are the contributions of the pair in the chemical bond for H2. So it bears a lot of physical information, but the energy is weakly dependent on that. So that's a delicate point, right? Because we'd like really to tell something which leaves a very low energy scale, okay? And so we need to be efficient in optimization, because we need to resolve very small energy scales, which are maybe completely covered by fluctuations, okay? But still, despite the fact that that's another amazing feature of this stochastic minimization, right? Despite the fact that at each iteration, the energy has quite large fluctuations, the knowledge of the gradients is much more refined than the total energy. So it's an information which is much deeper. And despite the fact that energy seems to basically be converged within the large fluctuations of the average of the energy at a given iteration, there is still room for improvement in terms of the wave function. Okay, so the sort of the gradients can see in the fog, if you like. That's what they mean. So they really can see in the dust. And despite you have a dusty and foggy weather, you find your direction anyway. Because you're not based on just what you see, but I mean the gradients tells you much more deeply about the system. Okay, and this amazing also steep descent level. So that's a feature which is present even in more refined method, but it can be appreciated here as well. Okay, so now to go beyond steep descent, to avoid this, to avoid the problem of having parameters very slow to optimize. And to accelerate those parameters, particularly, to have a more sort of balanced evolution of the parameters, a new method has been introduced, and that's also Sandro's merit of having introduced it. So, Sandro introduced this when he was working on lattice models way before attacking the ab initio problem. So the stochastic reconfiguration method. So let me explain how it is conceived and how it has been developed. So again, the key point, one of the operators you need to compute the derivatives is this O operator. So the derivative of the logarithm of the wave function, and by the definition of the O operator, you can Taylor expand psi at alpha plus delta alpha. So delta alpha is now the step in the parameter space. Delta, yeah, it's our delta basically. So the new wave function, which has this new set of parameters, alpha plus delta alpha, is equal to the former wave function with parameters alpha, but with this operator applied to it. So if you apply this operator to it, you get the wave function variation up to the first order in delta alpha. Okay, and so that's very easy to show because you Taylor expand your wave function, and then you realize that by playing with the logarithmic derivatives, you get exactly you can recast, if you like, the variation of the wave function along a parameter direction in terms of a product between the logarithmic derivatives times the wave function itself. Okay, due to the fact that these operators are computed as derivative of psi over psi. Okay, so you get this nice compact form for expressing the first order variation of the wave function in terms of these O operators. And but then we'd like to compute not the variation itself, but the variation normalized. Okay, so we'd like to normalize the wave function, although we don't do this in quantum Monte Carlo because you know that normalization basically drops off from the metropolism ratio, so you don't need to compute the normalization. But here we'd like to do to derive the formal equations, so we need to include the normalization properly in the equations. And so if you include the normalization, then the operator which takes into account the variation of the wave function normalized is not delta alpha times OK, delta alpha k times OK, but it's delta alpha k times OK minus OK average. So where OK average is the average of the O operator over the Monte Carlo sample. And so you see that it's also very nice because it shows that up to the first order in the parameter variation, you can express the variation of the normalized wave function in terms of fluctuations of the OK operators. Okay? OK minus OK average. Okay, the next step is to estimate the change of the norm. Okay, so sorry. Before this one was the one I introduced before was the new normalized wave function. Okay, so the new normalized wave function is expressed with this operator applied on psi alpha, the original psi alpha, and this new operator involves the fluctuations of the OK operators. That's for the new normalized wave function. Now I'd like to compute the norm variation between the former normalized wave function and the new normalized wave function. If I compute the norm variation, I should compute this object here, okay? Norm squared, actually, sorry, the norm squared variation. You can do quite straightforward your maths, and you realize that this norm squared variation of the two normalized wave functions, the new one and the old one, can be recast in this form here. It's the sum over k and k prime running over the parameter indices, delta alpha k prime times s k k prime. So this s k k prime is a key matrix in the stochastic reconfiguration. It's called indeed stochastic reconfiguration matrix, and it's the covariance between OK and OK prime. So it's the average of OK, OK prime minus the average of OK times the average of OK prime. Okay, and so this is a key matrix. You're going to see why. And yes, so then we realize that this covariance matrix for the stochastic reconfiguration is very similar to the Fisher information metric in the information theory. So so there is a parallelism with information theory which has not been realized before, actually, so since a couple of years ago. So now, what is the cost function of the stochastic reconfiguration? We have seen that the cost function of the steeper descent was to put here delta alpha k square, right? So divided by 2 delta. Here instead we have instead of delta alpha k square, we have a matrix. We have a matrix which is we have the wave function, the variation of the square norm of the wave function. So you yes. Yeah, it's definitely positive. Yes, it's positive definite. Yes, because it's a covariance matrix. Yeah. So you see the point here. So that's a very important point. So before in the steeper descent, I had here what was the term which was the binding term of my minimum was delta alpha squared. Okay, so in delta alpha squared there is no notion of the matrix of the wave function. So there is no so basically it's an Euclidean space of the parameter space. Okay, so the steeper descent treats the parameter space in the Euclidean way. Okay, there is no notion of a wave function behind it. Okay, the only notion the wave function, if you like, is in the gradients. Here in the stochastic configuration, the minimization is bound by the variation of the norm of the wave function. Okay, so that's a very important difference. And so by putting as binding term the variation of the norm, I'm able to precondition the gradients such that the variation of the parameters are optimal in the Hilbert space of the wave function. So the variation in the stochastic configuration, it's an improved steepest descent. It goes beyond steepest descent because we put information about the topology of the Hilbert space. While in the steepest descent, we just have the Euclidean space of the parameter of the parameters. And so once we minimize this cost function, we get this delta alpha. So we get this delta, the variation, the parameter variation is now delta, the step I choose, which is still a tunable parameter, obtained by computing the inverse of the S matrix, the stochastic configuration matrix, applied to the force, to the gradients. Okay, so the delta alpha, now the direction delta alpha knows not only about the gradients but also about the topology of the wave function, the topology of the Hilbert space. Yes, so this is a slide which summarizes the various possible updates according to the methods. So we have seen steepest descent, delta alpha k is equal to this tunable step delta times the gradients. Then we have this Newton-Raphson method is based on the Hessian. That's something can be doable in different schemes, but not in quantum Monte Carlo. So computing the Hessian is very hard. So computing also the curvature. And so if you like the intermediate method between the steepest descent and the Newton-Raphson, which is, if you like, the optimal one. So if you know the curvature, of the energy as a function of parameters, you don't know, you know not only the direction but also the length exactly. So you go directly to the minimum. The stochastic configuration is something in the middle between the steepest descent and the Newton-Raphson. Okay, but it's an improvement, a significant improvement with respect to the steepest descent. And this is, in the information theory, this is known as natural gradients minimization, and has been sort of proposed the first time in this paper in the neural network community in the 1998, while Sandro proposed this in the same year, but he was not aware of the other work in a completely different community. Okay. All right. So now there is one caveat. There is a point one should take care of when you do this, the inverse of this S matrix. The inverse, so the S matrix is stochastically evaluated, so it's noisy, and the inverse of a noisy matrix can be also ill-defined, and you have to regularize the S matrix by putting the easiest way to regularize it is by putting a positive constant term in the diagonal of the matrix, such that the inversion is more regular. So by regularizing this, you'll basically get rid of the problem of ill-defined inversion due to the stochastic, the noisy matrix. Yeah. So and you see that now, remember the energy before with the steepest descent, the energy converged after 100 iteration. Here the energy converged after 10 iteration. So the stochastic reconfiguration method represents yields one order of magnitude improvement with respect to the stochastic, the steepest descent. What about the parameters? So that was the situation before steepest descent. You see the very slow convergence of the lambda parameter, and here the parameter lambda in the stochastic reconfiguration is much faster. So you fluctuate, but you basically fluctuate around the mean value after 40 iterations. So it's much faster than the steepest descent. And this gain is particularly sizable for slow parameters. Okay, so you have a significant acceleration, particular for slow parameters. So you can see here that these parameters are fluctuating around the mean average. Okay, so this is an observation which is very important because to get the final parameters, you should average their values after the transient behavior. So you have a transient behavior, and then you have a regime where they fluctuate. Okay, they don't drift. So there is a regime where they fluctuate and they don't drift. If you should average to get the final parameters. You should average their value starting from the iteration where they stop drifting. Okay, this is an approach. So I mean, you could have also chosen to take much larger sample sizes at each iteration to have less fluctuating parameters here. So where this fluctuation comes from? So this fluctuation comes from the fact that at each iteration I do a new Monte Carlo sample. The new Monte Carlo sample is finite, so it's of course affected by an error bar, which is 1 over square root of the size of the sample, and so that's the origin of these fluctuations. So in principle, I can reduce these fluctuations by increasing the sample size. Okay, and so then now there is a trade-off. This trade-off is really something which depends on the system and also on your experience. There is a trade-off between the length of the sample size per iteration and the number of iterations you'd like to have. Because of course, I mean, in terms of CPU time, what matters is the length of the full simulation. Okay, and the length of the full simulation is the one which sets the wall time. Okay, now the number of iterations you can do given the full set of Monte Carlo iterations is given by the full number of iterations divided by the number of iterations per iteration, the number of Monte Carlo iteration per iteration of the parameters. Okay, so there are two iterations here. One is the Monte Carlo iteration of my electrons moving in the space. The other one is the iteration of the parameters. Okay, both iterations are stochastic. You can see the parameters move stochastically. Okay, I'd like to find a trade-off between the number of iterations in the parameters and their stability. So I'd like to move the parameters as much as possible. So I'd like to have the shortest possible sample length per iteration of the parameters. But if this sample is too short, the fluctuations will be too large here. And so I lose, then the fog will be really very dense. I won't see anything. Okay, to see through the fog, I need a little bit of statistics. Okay, that's the philosophy. To see through the fog, I need a little bit of statistics. I mean, a little bit, not that much. Okay, it's because the length of the quantum Monte Carlo sample is very short. It's amazingly short. I mean, that's how long is it? I mean, how large is it? It's about 50 iterations, right? I mean, depending on the complexity of the system, but you know, you don't have a very large quantum Monte Carlo sample. You don't have millions of electron configurations. You have just hundreds of configurations, and that's enough. But if you reduce too much this number, then you're gonna crash against the wall because they're gonna, I mean, so you should be really, there is a trade-off between the quantum Monte Carlo size per parameter iteration and the stability of the optimization. Okay. So optimizing a wave function is a sort of so it requires some skill. So it's not that easy. It's not that's so we developed the powerful methods, but it's still the step which is very delicate, and actually people like to avoid this as much as possible. Okay, so there are quantum Monte Carlo groups which believe much more in sort of relying on diffusion Monte Carlo, which is sort of automatically. The diffusion Monte Carlo can be seen as a black box way of optimizing the wave function, the amplitude of the wave function, not the nodes though, because the nodes are fixed. And those would like to optimize the wave function at most. So there are these two communities, and the wave function optimization requires care, requires some guidance. It's not easy, although once you have sort of, I mean, given the system, I think the parameters are quite standard at the end. But it's not. I mean, it requires. It's not. You know, the sort of the process you'd like to have in a black box scheme. Okay, so it's the place where the black box here is less evident for me. Okay, but on the other hand, optimizing the parameters provides you a lot of physical information. Okay. Because we can see here also in this H2 case, right? Because this very slow parameter bears a lot of information. So yes, there is this sort of approach based on optimizing the wave function with its complexity, and other approaches we'd like to import, which would like to import the wave function from DFT or CAS-SCF, or we have seen with Anthony, right, the CIPC wave function imported in the quantum Monte Carlo, and then you can want or don't want to optimize the parameters, and then you can go directly to diffusion Monte Carlo. Okay. So I think for solid state physics, optimizing parameters is very important. I'm going to see tomorrow, not tomorrow, we're going to see an example of how important is optimizing the parameters in the wave function to get some physical information of the system. Okay. Okay. So so H2 is quite easy. So a difficult case was the benzene dimer, and we've done this in 2007. And in that case, we got 10,000 parameters. So the size of the parameters to optimize, if you keep the wave function very flexible, is large, about thousands of parameters, so 10,000 parameters. But despite the fact the number is very large, we've been able to optimize the wave function thanks to this stochastic reconfiguration method. Okay, so now some concluding remarks about optimization. So the good news is that after the work done in the last, I think, 30 years now we are able to optimize the parameters in quantum Monte Carlo in a stochastic framework with a very high accuracy and in a very robust way, even a very large number of parameters. So it's very good news. And this has also been sort of backup by the developments made in information theory. So the other community basically arrived to the same conclusions about the best way of optimizing parameters for a non-trivial topology of a given space. So you can even have better methods than stochastic reconfiguration by exploiting the curvature of the energy landscape as a function of parameters. If you know the curvature, you can accelerate even further the convergence. And this is done with a hybrid method which grasps some information about the curvature. It's called linear method. I don't want to talk about the linear method because I don't have enough time, but that's just for your knowledge. The linear method sort of is able to on one side, it exploits the matrix provided by the stochastic reconfiguration matrix. On the other side, is able to get some information about the curvature of the energy landscape in the parameter space. So it sort of improves upon the stochastic reconfiguration. And then some work done by Andrea Tirelli, who's sitting here. He tries to import machine learning schemes to optimize complex landscapes into the Monte Carlo framework, and I think he coded the Adams scheme to use gradients to optimize the complex landscape, but the results are deceiving compared to the robustness of stochastic reconfiguration and eventually also the linear method. So, and Sandro was happy about that.
You have a mess.
Exactly. Yes. Okay, now let's move to the calculation of forces. That will be the last topic before lunch. Calculation of forces in quantum Monte Carlo. So we have seen that energy gradients are very important because they are the key to optimize the wave function. And so now, what is the difference between the parameters? So what is the difference between a regular parameter which enters only the wave function with respect to the Ionic coordinate? So we have seen that the Ionic coordinate in the Born-Oppenheimer approximation is just an additional parameter, okay? And usually the ions are kept frozen. But if you'd like to minimize the geometry, to optimize the geometry of a compound, you'd like to also minimize the energy with respect to the ionic positions. Okay, so we'd like to optimize, relax the geometry. So the geometry relaxation is extremely important, both in quantum chemistry, material science, condensed matter physics. So it opens a new world of possibilities like computing phonons in solids, and I mean, of course, relaxing, finding the optimal structures in different pressure conditions. So it's really, it opens new perspectives. So and relaxing the geometry was sort of a taboo for quantum Monte Carlo community for many years, because it was very hard to achieve in an efficient way. Okay, and so the wave function, the geometry relaxation has been sort of a very hard task, and basically we didn't have any geometry relaxation in quantum Monte Carlo for many years, and so only recently we are able to do geometry relaxation for non-calculations, also thanks to the work by Kozuke, and this thanks again to the improvements we have done in the last decades. And what are the difficulties behind that? So the first complication with respect to the simple optimization of the parameters of the wave function is that the ionic parameters enter also the Hamiltonian. Okay, the Hamiltonian, in the Hamiltonian you have the ionic positions. Okay, and they enter in the potential. Okay, of course they enter also in the wave function, right? Because we use a localized wave function. So the Gaussians are localized at the ionic centers. So also the wave function depends on the ions through the position of these centers. Okay, so the ionic positions enter both the wave function and the Hamiltonian. So to understand how this dependence develops in the gradients, we can start from the correlated sampling. So we'd like to evaluate the energy at the displaced position, ionic positions R plus delta R, and you have these terms to evaluate. So that's the correlated sampling, right? So again, those are the X are the samples drawn for a wave function sitting at R. And now these ratios are the weighting factors of the correlated sampling, and the local energy computed at the new positions R plus delta R. So that's the correlated sampling strategy. And so correlated sampling was the only way used to compute ionic forces till a couple of years ago. Okay, because the correlated sampling, as Umrigar pointed out, don't require necessarily the calculation of the derivatives. I mean, you can get the derivatives from the finite differences. Okay, so you compute the energy at R plus delta R, you subtract the energy at R, divided by delta R, you get the gradients as finite differences. So, and this R plus delta R, if computed with the correlated sampling, doesn't require the generation of a new sample. Okay. On the other hand, it does require the calculation of the full wave function at the new ionic positions. Okay, so so it means that for each component, so you should imagine. So how many components I have in the system? I have 3 n components, right? Imagine that I have n or n ions. For each ion, I have 3-dimensional directions, so I have 3 n components. So to get the gradients at position R, I should compute these 3 n times. Okay, so I pay a factor of n for each gradient calculation, a factor of n times the cost of my variational Monte Carlo calculation. So I pay a factor of n more than the regular energy calculation. Okay, so that's why geometry relaxation has been sort of hampered because it was too costly. Okay, so with this scheme, which is still doable, and it has been used in some cases, with this scheme, geometry relaxation costs a factor of n more than the regular energy calculation. And as in quantum Monte Carlo, energy is already consuming, time consuming, forces have been even more time consuming. Now, we'd like to go beyond this scheme. A little bit the story of the wave function optimization. Right? We started also in that case from the correlated sampling, and we found better methods. So, also in this case, we start from correlated sampling, and we'll find better methods. So by differentiating these with respect to delta R, we obtain the contributions of these the gradients, right? So the final differences, and so we're going to have the Hellman-Feynman contribution plus the Poulet contribution. Now, the Hellman-Feynman can be written as the average, the stochastic average over the quantum Monte Carlo sample of the derivative of the local energy with respect to the ionic positions. And this involves the derivative of the Hamiltonian, right? Because the local energy is h psi times h psi divided by psi. So this will involve the contribution from the Hamiltonian. And then I have the usual Poulet contributions, which are well known because these Poulet contributions are the same we found before for the parameters of the wave function. So we have the covariance of the logarithmic derivative operators and the local energy. So these terms, if you remember, half an hour ago, we have found these terms for the derivative of the wave function parameters. Those parameters which don't enter the Hamiltonian. Now we have also the Hellman-Feynman because now the Hamiltonian depends on these parameters as well. So that's the complexity. So the complexity between, if you like, the additional term which is present now here for the ionic forces, and it was not present before, is the Hellman-Feynman contribution, while the Poulet was present also before. Okay. Okay. So yes. So in principle, you should displace the ions. Okay. And in the new ionic positions, the wave function is not optimized. I should have another contribution, because if I don't optimize the wave function, I have also the contribution coming from the dependence of the parameters, the wave function parameters, with respect to the ionic position. Okay, because the electronic parameters follow the geometry. So the wave function shape changes as a function of the geometry. If I change the geometry, the wave function will change as well. Not just because I change the centers, but because I change also the chemical bond. So it's not just the centers we will change, the ionic centers, but we'll change also the parameters of the wave function, like the lambda or the A, B, Jastrow factor, and so on and so forth. So I will have an intrinsic dependence of the wave function parameters on the ionic positions. So how to deal with this? So this will make the problem even more complex, because I have not only the Hellman-Feynman, but also the additional term, which is it's the chain rule here, the derivative of the local energy with respect to the parameters times the derivative of the parameters with respect to R. So so that's the contribution coming from the parameters dependence on the ionic positions. So this will make the situation very hard to deal with. So to get rid of this parameter, what I should do? I should optimize the wave function at the new ionic positions. So if I optimize the wave function consistently in a separate way, this is zero. And if I start from a wave function optimized at a given ionic configuration, this is zero. Okay, so that's the derivative computed at the starting point for the configuration R. So if at a given ionic position, my wave function is fully optimized, it means that I don't have any more this dependence. Okay. Sorry, because this is 0. Okay, so the term which is 0 is this one. So if the wave function is optimized, the derivative of the energy with respect to alpha is 0 at a given position R. So this is solved. Okay, so this is solved as long as my wave function is well optimized. Okay, so this term doesn't appear in the gradients. Okay, now there is a second problem about the calculation of these ion gradients, the forces. And the second problem is that the estimators are they have infinite variance. Why is that? They have infinite variance mainly for the reason which is related to the fact that I have a nodal surface. Okay, so how these operators look like. So if you take, for instance, this O operator, right? It's a logarithm derivative of this kind here. Let me find this in the slides in an explicit way. So it should have a way where so those are the O operators, right? So the O operators, we have the derivative of, now we should replace the derivative with respect to alpha with the derivative with respect to the ionic position. So yeah, now I have alpha is replaced by R, okay? So I have the derivative with respect to R of psi alpha R, depending also on R, divided by psi alpha R. So you see that these operators are divided by the wave function itself. So you know that the Fermionic wave function has nodes. You have seen the meaning of nodes, I think, with Claudia and Anthony. So it's the nodes are the place in the space of electrons where the wave function is 0. Okay, so if the wave function is 0, I have a divergence here, 1 over 0. Okay, or something constant over 0. Okay, so I have a divergence, and so that is true not only for O but also for the local energy. The local energy is h psi over psi. So once I divide by psi, if psi if the configuration falls on the node, the psi is 0. So also in that case, I have 1 over 0 divergence. And in particular, as I compute the covariance between O and E, and also this derivative here. So the divergence of these is of the order of 1 over n squared. Okay, so so it means that the average is still fine, but the variance, I should take the square of it. The variance goes like 1 over n to the 4th power. Okay, this one. And 1 over n to the 4th power is a divergence which is not bound in the 3-dimensional integral. So it means that the variance diverges. And so this is a very bad situation, because to define properly a correct, a valid quantum Monte Carlo estimator, I should have both average and variance well defined. Okay, so if the variance is not well defined, my Monte Carlo estimator is meaningless. I need to have the variance to determine the error bar on an estimator. Otherwise, any stochastic evaluation of it is meaningless. So how to solve this problem of the infinite variance? Well, I can use again the reweighting technique. Okay, so I can use the reweighting technique. So I define a pi distribution, a new distribution, which is defined by well, I should put so it's defined in that. Sorry, that's not pi. Yeah? This W. So that's the reweighting factor. It's not the distribution. So this W is defined as psi squared over R. Okay, where now R goes to 0 in the same way as the wave function here. So the wave function goes to 0 as n squared, where n is a distance from the nodal surface. Okay, so it's a distance here. So this factor here corrects, compensates for this vanishing behavior of psi squared. And so it means that on the node, this doesn't go to 0, is finite. Okay. So then I can compute. So as I divide this by R, I should multiply also the operators by R, right? So I divide by R the distribution, and I should multiply the operator by R. So it means that now the operators are multiplied by an object which goes to 0 when they diverge. Okay, and it goes to 0 with the same speed as the inverse of the divergence. So this will be finite as well. So by curing the vanishing behavior of psi at the nodes with a compensating factor R, I'm able to get the distribution finite at the nodes instead of being vanishing, and I'm able also to get the operators finite while they were diverging before. Okay, so I cure this divergence, and I am consistently including this correction into the distribution to get an unbiased estimate. So I have an unbiased average. Okay, I got an unbiased average for these operators with the finite variance. So I solved the problem. Okay, and okay, so and to choose R of X, I use basically the information of the determinant through the matrix of the determinant of the Pfaffian. So I use the entries of the matrix as a way to estimate the speed of the vanishing behavior of the wave function. Okay. So now I can ask you a question. So here I talked about this divergence, right? This for the gradients of the energy with respect to the ionic position, so the forces. So this was a problem, and this problem affected both Hellman-Feynman and Poulet contributions. So why I didn't speak about the divergence when I talked about the Poulet terms for the parameters optimization? Why why I'm worried about the divergence of these Poulet contributions here when I vary the ionic positions, and I didn't talk about the divergence of the Poulet contribution in the case of a parameter optimization. The Poulet contribution is the same, right? Is the covariance of O times E, no? The logarithmic derivatives and the local energy. So, and that's the Poulet contribution. And I'm telling you that the variance is infinite for the force optimization, but I didn't tell anything about the variance of this contribution in the case of the parameter optimization. Do we have an idea why for the parameter optimization I don't have this problem, while I do have this problem for the ionic optimization? Indeed, I could have the same problem also for the parameter optimization, but only for some set of parameters, not for all parameters. So I could have a problem for the parameter, the same problem of the unbound variance, even in the Poulet term for the parameter optimization, but only for a subset of parameters. Those parameters which change the Slater determinant or the determinant of the nodes. So if the parameters, so there are parameters will in the wave function. So the parameters which enter the Jastrow don't change the node, right? Because the Jastrow is a bosonic wave function, doesn't have any sign change, so it doesn't have nodes either. Okay, while the determinant does have nodes, because the sign structure is not trivial, and there are parameters which affect the nodes, because there are parameters in the wave function which change the node location. So it's exactly when I change the node location that I have the problem of divergence of variance. If I don't change the nodes, I don't see this problem. And the reason is that if I don't change the nodes, the Monte Carlo sampling vanishes at the nodes. So I will never have signals from the nodal divergence in a Monte Carlo sampling, because the nodes are frozen and the sampling will be vanishing small. The probability of sampling the nodes is 0. All right, so that's the reason why the Poulet terms, the variance, the Poulet terms doesn't diverge for the parameters which don't change the nodes, while it still diverges even for the parameters optimization for those parameters which change the nodal structure. So the geometry optimization is delicate, because when I change R, I change the nodes, because I change the location of the one body basis set, right? So this it's a situation where I change I change dramatically the nodal location, because I move completely the basis set centers, you know. So that's why in the optimization of the geometry this is particularly relevant. Okay. And then there is another one, which is the third problem, which is I need the additional source of infinite variance due to the derivative of the potential. So if you take the derivative of the potential, you get this. The electron ion term, you get this 1 over r square behavior, right? And so this one is also has also an infinite variance, and so to cure this term, I use what's called space warp transformation, introduced by Umrigar 20 years ago. So this is easily solved. So in the sense that I move an ion. So imagine that I have generated my Monte Carlo sample. Okay, I have take an electron configuration. Electron configuration, take an electronic cloud around the nucleus. Okay, so I have a configuration which sort of is representative of the electronic cloud. So I have a distribution of electrons around the nucleus. I move the nucleus. As soon as I move the nucleus, the electronic cloud sampled before is completely misplaced, because it's no longer centered around the displaced nucleus. It's shifted. So to benefit from the previous from the sampling of the previous wave function, I should do a coordinate transformation. So I transform the coordinates such that the transformed coordinates follow the shift of the nuclear shift, okay, such that they are still distributed around the nucleus in a meaningful way. Okay. The price to pay is they have to compute the Jacobian transformation. So there is a Jacobian in the integrals we should be taking into account. Okay. And so by following by shifting the coordinates around the nucleus, the electronic coordinates around the nucleus, I'm able to preserve the variance of this term here. Okay. The point is that in this case, the shift is really atomic. It's not macroscopic. So it's really around the nucleus I'm moving. Okay. So that's why the transformation is weighted by a function which is localized around the nucleus I'm moving. Okay. So that's the third trick to deal with another source of infinite variance. So it's a mess. It's a very complicated problem. So anyway, this has been solved with these different steps. Okay. So we have a way to cure the divergence coming from the potential, from the nodes, and finally we can run the dynamics of liquid hydrogen, and you can see that the Poulet term now is under control. So the red, so it's very hard to distinguish between red and green here. So the red points are the points before. You see the huge fluctuations. So this infinite variance is shows up in these very far apart points. I mean, there are points which are really outliers. You have outliers. So you have the majority of the points are sort of they are distributed around the average value, which is still a computable quantity. But the variance is sort of diverges because you have outliers, very few outliers, very far apart. Okay, so that's manifestation of the infinite variance. While when I use these reweighting techniques to cure the nodal divergence plus the space warp to cure the potential divergence, I get a very nice steady behavior without outliers. Okay, so now you can imagine that I have 5 minutes and then I'm done. I'm dead. You can imagine that taking into account all these details is very complicated because I have to carry out the derivatives of these complex change, Corrian transformation. The wave function distribution is modified, and this depends also on the ionic positions. So everything, I mean, you have many terms, which contributes to the calculation of the ionic forces, and also many terms which correct for these divergences appearing in different locations. So I have, I have a complex problem, and to derive this properly is a huge task. And in the TurboRVB code, this has been done using a very clever and sort of efficient way, which is the adjoint algorithmic differentiation. Okay, so I mean, it's sort of in a nutshell, it's basically exploiting the chain rule for derivatives in sort of in a way which is handleable more easily in terms of programming. And the main objective for using adjoint algorithmic differentiation is to separate all the tasks which basically which lead to the evaluation of the local energy and the logarithm of the wave function in a structured way. Okay, so you should divide this process task by task. So what is this process? This is basically the main process of any quantum Monte Carlo code at the end. Because the difficulty of any Monte Carlo code, quantum Monte Carlo code, at least the Monte Carlo code we are doing here, is to get the local energy given the electron configurations, given the parameters of the wave function, and given the ionic positions. Okay, so computing the local energy on the electronic configuration is the fundament, and not only that, but also the logarithm of the wave function. These two quantities, these are the fundamental step of any Monte Carlo code. And so this should be optimized, in a very careful way to enhance the performances of the code. So in the TurboRVB, this has been divided in tasks, 11 tasks, and for each one, then you can apply what's called adjoint algorithm differentiation to compute finally the derivatives of the local energy and the logarithm of the wave function with respect to the ionic parameters, such that the forces evaluation is possible in a way which is efficient. And that's the final slide, which shows that while for finite differences, I pay the factor of n to compute ionic forces, thanks to the propagation of derivatives, which are computed locally for each ionic configuration without finite differences, I basically have a speed up of factor of n. So I can compute ionic forces with the same computational cost as the one used to compute local energies. So for all 3n components, okay? So the cost of computing 3n components for the forces is not, doesn't scale with n times the cost of the local energy, so it stays the same cost as computing the local energy. So geometry optimization becomes affordable even in quantum Monte Carlo. And not only that, but also phonon calculations and all the structural properties of materials which are of interest in material science, for instance. And with that, I thank you for your attention. I don't know if you have questions at the time. Yeah. Yes.
Let's say in the principle, this derivative could be also used to optimize node. Okay.
Yes. Yes, because yeah, to optimize the nodes, you should probe them, right? So you should be able to access the nodal region. And I think that's a good idea. I think, Kozuke, in your recent paper on the node optimization for the diffusion Monte Carlo, yes, do you use a reweighting technique, right? Or not?
It's very similar. It's really the
so you optimize the nodes in diffusion Monte Carlo? No?
Yes.
Not published yet. Okay.
Okay.
So, unpublished. Confidential information. Ah, yes. Mm-hmm. Mm-hmm. Yes, yes. So that's a very good question, because indeed, so the scaling of the error bar on forces is the same as the scaling of the error bar on energies, and yes, so. And unfortunately, the scaling of the error bar of energy is extensive, because we're talking about total energies now. So, so this is indeed a good point. So, in terms of fluctuations, forces are objects which fluctuate a lot. So, in terms of computing efficiency, I mean, we are able to stay with the same cost as the energy evaluation. In terms of error bar, both scale with the system size. So the next step indeed is to exploit locality to make forces not scaling, to make the error bar of forces not scaling with the system size. This would be great, but it's not achieved. It's not achieved yet, unfortunately. Yes. Yeah, and there are indeed people working on that. So the idea is to exploit locality to sort of yes, to make this error bar scaling, not scaling with system size, but scaling only with the environment, which is localized and not extended. But this is critical for extended. I mean, it's not critical for molecules, right? Because for molecules, you don't have this problem. But for solids, we do have this problem. Yeah. For solids, we do have this problem. So in that case, the only thing to do is to increase the sample size. The sample size must be increased with the system size. Yeah. Yes. Yes. Ah. Yeah. So. Yeah. So one of the reasons why just correlated Geminals is appealing is because we avoid this expansion in multi-determinants. Okay. So again, for molecules, this should be okay. I mean, for molecules, I mean, if the number of relevant states is still reasonable, it's okay. But if you trust, I mean, if you use the idea of expanding the wave function in the determinantal space, is the later determinants, and you apply this to our quantum Monte Carlo, this real space quantum Monte Carlo, I don't think it's a good idea. I mean, the problem is that you lose the benefit of real space quantum Monte Carlo, in the sense that you're paying a cost which is in principle exponentially growing if you sample properly the Slater determinant space. I mean, CI, is exponentially growing. So you don't want to follow CI in this framework. You would like to be orthogonal to CI. So if you follow CI, you're going, I mean, this becomes completely useless unless you'd like to, to recover the milli-Hartree difference, which is still left because CI is not complete. But so then if you use a multi-determinant framework in the wave function, then you should play either the filter scheme by Antony, who selects the most relevant determinants, and then you end up with, instead of millions of determinants, you end up with a manageable number of determinants, like 100 or 1,000, but not more than that. Otherwise, you lose the benefit of doing quantum Monte Carlo, because you're going to pay the same exponential trade-off as the theories, the quantum chemistry theories, like SSCF or other theories, where there you have the advantage of being deterministic, like you don't have the noise. So yeah, so this is a little bit you should really find clever wave functions which are able to describe in the best way the nodal surface, or you'd like to optimize the nodal directly. This will be the final dream, right? To optimize the nodal surface in diffusion Monte Carlo. This will avoid cumbersome multi-determinant expansion, because you'll find the optimal nodal surface, and this will be basically the solution of the Fermionic same problem at the end. What is the advantage of the Geminal? The Geminal is you are still basically evaluating a single determinant. It's not a Slater, but it's still a single determinant. So it scales polynomially and cube with the number of particles, while keeping all the correlations, because you don't have the full correlation of CI. It's clear, right? But you have correlations from the Jastrow, you have correlation from the resonances, And then you have the correlation from diffusion Monte Carlo. When you project the wave function, you have the correlations, the optimization of the amplitude of the wave function, while keeping the nodes, the ones provided by the geminals. Yes, so I mean, this is my viewpoint on the story, which is the one by Sandro anyway. So maybe I'm biased by Sandro's view because I grew up with Sandro, and but I think there are several reasons why this should be. I mean, the main reason I told you, right? Because you don't want to play the same game as sort of the expanding this in the determinant space. Although there are Monte Carlo, the full scale quantum Monte Carlo is exactly meant to sample in a clever way, in a stochastic way, the determinant space. And that's the way to go if you like to sample the space. So if you'd like to expand your wave function in the Slate determinant space, you would better go with the full scale quantum Monte Carlo, not with the space quantum Monte Carlo. Okay.
The optimized parameters.
So long depends on system size.
Like
another size, same materials. Okay, so no, I mean that's so the question is how the parameters depend on the system size. So they don't depend too much because we are using a localized basis set. Okay. So the localized basis set has the advantage that you keep locality, the information locality in the wave function. And so if the wave function is well suited to describe correlations within a given range, you extend the system, you embed your cluster in a larger system, the correlation within your cluster stays the same. So the fact that you use a localized basis set makes the wave function transferable. And that's a very important property. It's a very good question. The second one was about
like one set for ground state and other.
Yeah. In that case, yeah. So if you go from ground state to excited states, the wave function, the parameters can change a lot. Particularly the parameters involving excitation. So I don't think in the case of, for instance, of solid state physics condensed matter, so I don't think the core states will change a lot, but all parameters involving the excitation space will change. Yes, definitely. So in that case, unfortunately, the parameters should be changed, should be optimized the given symmetry or the given excited state. Okay, thank you. I think we can close here. Yeah, other questions? Yeah.
Just open lunch. Then
Yes.
let's say we have a 1.5 month.
Sorry?
Would you send the PowerPoint slide? Because in my tutorial session, I read to refer to you.
Yeah, sure. You sure? Yeah, I send you the slides. Yes, sure. Yeah.
Sure. Let's get it started.
Yes.
Okay. So, hello everyone. My name is Kosuke Nakano. Actually, I'm from Japan, but now I'm studying this. I'm kind of visiting research in CISR. So I'm working with Sandro now. And today I am talking about TurboRVB and Turbogenius overview and workflow. And I will give you the tutorial session to understand, let's say, the TurboRVB, the theory implemented in TurboRVB more deeply, let's say. So first of all, this is outline. So first of all, I will explain overview. Let's say I will talk about the overview, and then go on the hands-on session. So first overview. Okay. So CISR. So we are developing the two. Yeah. Yes. Sure.
So will you keep the URL of the tutorial website
Yes. I mean, I will ask you all to download the HTML files to your local laptop. Oh, So okay, we have so we are this. Ah, okay. So this one, for example. Does it work? Okay. So we have two packages inside this TurboRVB package. One is TurboRVB, which is actually the QMC engine to run, let's say, VMC calculation or diffusion Monte Carlo calculation, as well as let's say, DFT calculation. So, but this is Fortran package, let's say. So, yeah, like Quantum Espresso or Win2K and so on. So now we are also developing this named TurboGenius, which is kind of a wrapper, let's say helper. That this is very useful. Let's say in my opinion, I launched this TurboGenius package to make TurboRVB more user friendly and more, let's say, useful for users and also professional users. So today's tutorial is based on this TurboGenius. TurboGenius allows us to generate input file, analyze output files, and for example, also submitting jobs and collecting jobs from the cluster machine. So, okay. Let me see. So, okay. So the paper, we have already published TurboRVB paper. So if you're interested in the details of the implementation of TurboRVB, you can refer to this paper and also our website. You can Google TurboRVB. You can see our website. Okay. So, but now I am writing TurboGenius paper. So, and okay. So one of the important questions is where can we download TurboRVB, right? And TurboGenius. Unfortunately, at present, TurboRVB and TurboGenius are our in-house code. So they are not open source code. But so please do not distribute it to the public. But I will, if you contact me, okay, this is my email address. I will give you the permission to download TurboRVB and TurboGenius from CISA GitLab server. This is actually internal GitLab server in CISA. But you don't have to do that today because I have already compiled TurboRVB and TurboGenius on Košice supercomputer. So you can just copy Košice sheet. It's a bit difficult to pronounce. So I will tell you how to, copy and copy the files. Okay, so actually this is just an overview. So let's move on to the session. So and Otto and Abhishek. Okay. Will also help you with, let's say, doing tutorial because they have already traced my tutorials. So okay, so let's go to move on the hands-on session. So first of all, would you log into the Košice? So and would you open this text file in which I put all the command to copy, let's say, TurboRVB or TurboGenius and so on. This one. I hope you have the permission. You don't have a permission?
No, I mean the applications and then application again.
Yes, and that is okay.
It's twice application?
No. You should open this text file. Yes, it's the type. It's probably you're going to, yeah. Someone is stuck. Okay. Please don't edit it. Just copy it. No, just open. Just open. Just open or copy. Copy to on, let's say, yeah, Košice machine. Košice. Okay. Someone is stuck. No. It's okay.
This is just helpful us deciding what commands we need to just.
No, you don't have to do the, sorry, the memo. Yes, okay, memo properties. So first of all, you should, okay. Okay, first of all, would you add this path to your bash? This one. So first you should open this .bashrc, and then would you add this export path equals blah blah. This is the path for TurboRVB binaries. Okay. No, you can copy, let's say, the, so yes, this is the text file that I have asked you to open, so you can copy and paste the line. Okay. Okay for you. It's fine. Okay, sure. Sorry. Okay. Thank you. Okay for you? Okay, okay. So, and then use. Thank you very much.
The mic? You should do it.
Yes. Okay, and source. What? What is this?
Try again.
Okay, so after you add the export line, you should source it, and would you try if this which TurboRVB serial.x works? If it works, you can you have successfully added the path. Yes, path the TurboRVB serial. Which, yes, this one. Which, oh. Okay, here, which serial, TurboRVB serial works, okay? It doesn't work? Yeah, sorry, did you add this line in bashrc?
Just copy the whole line.
Yes. So do you know how to use VI, for example, or EMAP?
Sorry. What should?
Okay. Sure.
No, it's
fine. Oh, that's no problem at all.
I can send it to you.
It's okay. Okay, for your information, today I will not tell you how to compile TurboRVB, but let's say contact me. Please contact me if you compile TurboRVB on your laptop or on your cluster machine. Yeah, either let's say one of us, let's say, will help you with the CMake and also make.
Which TurboRVB.
Yes.
And
V
hyphen
serial
dash.
Or you can copy the, let's say, the line in the file. So you can open, let's say, two tabs if it is possible. It is possible to.
Yeah, it is put table. It is possible.
Okay. So do you know how to do it?
You can open another
one if you want to have it as a reference on the side.
Yeah, sure,
That
sure.
would be very
It's very helpful, right?
Yeah,
For copy and paste, yeah. Especially you are not sure how to use VI. Okay, if you have done this TurboRVB setting, so let's proceed with this KN file manager setting. This is actually kind of Python package I made for help people with submitting and collecting jobs on the cluster machine. Actually, you don't have to use this one, but I mean, for let's say, making this tutorial as smooth as possible. So I will use this KN manager. But for your TurboRVB run in your, let's say, research project, you don't have to use this one. Okay, so first of all, you should copy. So you should go to the current directory. This one. So would you done? So would you do these commands? Okay.
Not necessary to go to home directory.
Here.
It could be in any folder where you want.
Yeah, any folder. Yes, any folder. Yes, any folder. Yes. Because this is Python package, so we are going to do pip install. It's okay. Yeah, sure. It's okay. So okay. So from now on, we will load, let's say, modules pre-installed on a supercomputer. So we are going to use Intel compiler because I have compiled TurboRVB with Intel Fortran, this one. And also, would you load this Python 3.85, which is needed for TurboGenius. And CMake, sorry, CMake is, strictly speaking, is not needed.
Yes, but if you change the folder for the TurboGenius, you need to also be inside the folder when you do the pip, because there is a.
Oh yeah, sure. So yes, I thank you very much. And then after you load these modules, please do pip install PySCF. But this is, you know, PySCF, right? The DFT, Python DFT code. Now, thanks to TREX.io, probably Anthony or Claudia explained, we can use PySCF calculation as a starting point of TurboRVB. So we can generate wave function using PySCF, and then we can proceed with the VMC or DMC optimization calculations. So please do pip install and pip install TREX.io here. Okay. Slightly zoom. Okay, sure.
it's visible nicely, but just
sorry, I cannot zoom it.
Is it?
No. Why? I mean, Control plus.
No.
Okay. Thank you. Thank you very much. Yeah,
Should be enough, right?
Yes, it works. Thank you. Yes. Thank you. Okay, every PP is so fine. Do you have a question? Sorry, you. No problem. Okay. So, and next, would you go to the directory, TurboGenius directory? You copied TurboGenius, right? So here you should go to inside the TurboGenius directory. If you copy TurboGenius to your home directory, this command should work. But if you do not copy the TurboGenius to your home directory, sorry, you should go inside TurboGenius directory where you installed. Which one?
It's missing an argument.
So I mean,
Dot.
No, dot.
there's a
Dot.
I didn't see the dots.
And after you go to inside TurboRVB directory, so TurboGenius directory, you should do this pip install -e period. Don't forget period. It works. Okay. Sorry. A space period. Yes, space period. Space period. Yes. Space period. Yes. Oh, so which one?
The installation takes a while.
Ah, okay, okay, sure.
So we have to
Exactly, yeah, sure. Okay, sure. So after your installation finishes, you should copy this file, the current the home directory. This should be home directory, okay? This. And then would you try to check if TurboGenius works by this command? If you see help, a lot of helps, it means that okay, you have successfully installed TurboGenius on your supercomputer. So maybe it takes time, right? Okay.
It's just taking a while.
Okay.
TurboGenius
TurboGenius installations. Now you're installing TurboGenius. Okay. You're waiting. Okay. Sorry. Works? You're now installing. Okay, installing. Okay, good. Works? Now you are now installing. Okay, all the modules. Okay, sure. Okay, sure. Sorry. Oh, sorry, I forgot to mention. Today, I am giving you the tutorial about hydrogen dimer, which is the most fundamental, but almost comprehensive. It includes all the necessary tutorials to do some realistic calculation in your research project using TurboRVB. And tomorrow, I will give periodic boundary condition calculations, because Michele or Ivan probably will explain somehow. Will explain how to the periodic boundary condition calculation are implemented in Turbo. So completed? Oh, still working. Sorry. It's still working. It's going on now.
It's fine.
Fine.
Oh, that's fine.
Oh, it's fine. Okay.
Still.
Still fine. So it takes time.
I think you were doing it.
We are waiting for TurboGenius installation.
Wow.
You have a problem?
Yeah, I think if you just command line to put the user guides.
Oh, really? This is.
But for me, it was not the case. So that's strange. I was
You belong to the indicated user.
Need to double check the problem. I don't think for problem.
That's
Please raise your hand if your installation is still going on. It's done? Is going on? No, sorry. Done. Going. Okay, sorry. So wait. So I've checked. Did you experience permission denies when copying the manual to your local directory? This one.
Really?
But Git object, I don't think we have to care about that, right?
Yeah. No, I also got this. You can.
Okay, sure. Thank you. Done? Not yet. Okay. So if you have already done the TurboGenius installation, please do these lines to copy. Let's say to install the manager project manager. Just copy and paste these lines. Okay. No, sorry, not just copy and paste. Until here, just copy and paste, and you should edit this. Yes, sorry. This you should edit this file. Machine data _yam, in which you can see this roster name, your username. Would you replace this encode? This is my name with your username. Let me see. Done? No. Okay. Sorry, sorry, TurboGenius installation takes a long time. I'm sorry about that, but no way.
No, the installation is like without errors, so that's important.
Important, yeah. Okay, still no problem.
I did this. I also edited the file, but then
Command not found. You probably you have not done this pip install.e inside file manager directory, right? Sorry, did you this one? This pip install e? No, not TurboGenius. For file manager. Here, you see file manager, current directory, file manager. Inside file manager, yes, you should do pip install. Yes, you should do current directory, file manager, pip install -e.p. Yes. Or you have not installed the file manager.
I have TurboGenius.
No. TurboGenius is different from file manager. So you should do twice in different directories. Yeah, okay. Yeah, that one. Yes. Okay, sure. I'm sorry about that. Okay. Wow.
So the thing is, so you change this so that it works.
Yeah, but it says that
no such file. Wow.
So the thing is, first you have to get it. You don't change it here because you are trying to get that file in your home directory.
I'm following the instruction, and
yeah, no, but here you don't have to change anything. Just
okay. So that's what I was asking.
Sure. Works? You are now installing?
Yeah, file manager and now I'm changing.
Okay, sure. Yeah. Thank you. And the file manager help works?
Yep.
Okay, thank you. Oh, really? So probably many people are now using the login node at the same time. So probably it takes time. Why? Okay, so you should replace Enkosuke with your username. Okay, done now. Thank you. Done. Yes, okay. Done. Done. Heterogeneous installation still. Oh, I see. Sorry. Only this Python package takes time.
Everything?
No. Just heterogeneous. Just heterogeneous. Okay.
The next step after installation, because I lost install is here.
Yes, here. You did. Yeah, you did this one, right? You should copy this temporary file. Yes, and then try to. Would you check heterogeneous -help works? This is a problem. I didn't suffer. I didn't expect the. No, the heterogeneous installation takes. Yeah, because now, all the people are using the same login node, right? Yes, this is the
But
problem.
it's almost done, so now.
It's almost done. Okay, so.
I will have the proofs of the paper.
Oh, really? Thank you very much. Yeah.
So
you're going to.
it will be online.
Online. B.
B-O-I.
Not PRL as we go.
Done? Ah, now it's done. Okay.
No, without sound. I mean, I think sound might.
You can open there's another tab to see my text file.
Yeah, it is.
Oh, okay, yeah, sure. And you should copy the URL here, pip install E. So you should copy this temporary file. No, this one. And this people, yeah, you have to do this one. Copy R. Just copy and paste. Yes. No, this one. Copy. Yes.
And
this should be the current the home directory. Yes. Oh, no. Yeah, I understand, but you don't have to change. Yeah, and yeah, sure. No problem. You don't have to change. Yes. Yes, this is my user guide. Let's say you should copy the user guide inside whatever. Not necessary. Yes. I will ask you to download this user guide to your local laptop. So, heterogeneous installation has been done.
The change is just in the user, right?
Yes, and that's all. Yes. Heterogeneous installation is done.
The second people install add-on successfully. This.
Yes.
But I'm using other. I'm using.
Oh, I see. So would you go to inside this file manager?
Yes. I have no problem. I have no problem. I know.
Okay. This one.
Now I'm going to.
Okay. You don't have to change the path.
But I.
Yeah, I understand. Yes. Understand. But you don't have to change it. Yeah.
So for example, instead of this, I switched to day 3.
Yeah, I understand. But you don't have to change this path.
Okay.
This one you just copy and paste. Yeah. Because this is some environmental file. Yeah. Works. Okay. Oh, no problem. You don't have to worry about that. Yes.
These lines here, and it opens this.
Which one?
This, I think it's the second last line that you've highlighted.
Okay.
And it seems it opens this. That surely isn't right, is it?
Oh, no, sorry. You should go. Would you close this one? This is VI. Okay, so you should go to. Yes. Let me check. Oh, next.
Yes.
Oh. Q. Once I try the next one. I'm sorry. This should be my name. No?
Oh, I thought we had to change that. Okay. Thank you.
Yes.
I arrived until here, it works.
Mm-hmm.
And if I do this, I just get.
No problem.
Okay.
This is some permission for the kid.
If I do this, it just tell me that.
Make
No, because it make me go outside other directories.
I understand. Make dir P. So hyphen P. No, sorry, not underscore.
Hyphen like this.
P space.
Yeah.
This should work. Okay. Because just because you don't have data directory. Sorry. Sorry, you should here not make dir tilde, is make dir hyphen P. Yes. Otherwise it doesn't work. Sorry. Here, after you copy this TurboRVB user guides to your home directory. This is the final line. Tutorial. We are tutorial.
So this means that there is something, you know, like that's the stage. So if there's something where the but I don't know more. Oh, yeah, there's some also understand. Maybe different reason. Now, so I have here, equal the concept.
Okay, so if you download everything, I will ask you to download this user guide. You have already copied this user guide, right?
So you already done this first step. It's really common. Copy to RVB user guides. This is the top of the file. And the same command is also here. It's redundant here. Redundant because it's also in the file.
Oh, I'm sorry. So, you don't have, you don't have. You don't have. But anyway, after you copy your this terrible user guide, I would like to ask you to download this file to your local. Because this user guide actually includes everything. Manual, tutorials, files.
Yeah, you put this in correct. Actually,
Yes. But the point is not let's say not everyone is using Linux. No. Someone is using Windows. Windows. Okay, Windows. Oh, it's fine. Machine here. Okay, so
we should download this user guide to your local machine. So please do this command on your local machine, not on my host.
Because somebody doesn't have the cookie as the copy the code file.
Ah, okay.
So in that case, it is dash R and then capital V and then the port because you have a special port that is 55 and 8. So
Right, somehow.
yeah, it's
this is only one missing part.
dash V and 55 and then P.
So minus P. Oh no, that's 5.
So no, and then it doesn't matter. We have to do like this. We try dash RP.
Dash P 552.
Yeah, and then the IP address will go. Just type IP or something.
No.
This is like the IPSAS. So you should do this command in a local laptop. Download the command. Yeah. Let's say okay, I would say that you're looking from every different thing. Let's say just for this program. Okay. Okay. So let's download all that. I don't know. If you download it, would you open the? Would you go to, let's say, tutorials? I'm not sorry. This file. If you download TurboGenius manual to desktop, you can open this HTML file. Desktop, Turbo user guides, build HTML, index HTML. This is the manual. And if you open the HTML file, you can see the tutorial.
Yeah, sure.
You have the download, so you move to the computer again and copy this the first tutorial file. So first you should go to let's say you're here, you should go to data, current directory, have tutorial that you made, and then you copy this file after just copy and paste, just copy and paste these two lines. Okay, to make it. Okay, these three lines. Copy the first speaking to the